Welcome to the History of Climate Science Ideas and Their Applications Conference. My name is David Warrilow, and I am a former president of the Society. This is the first live meeting we have had since COVID restrictions were lifted. On behalf of the Royal Meteorological Society, I offer a warm welcome both to you in the hall and to you joining us online. Unfortunately, I'm having to self-isolate, and so I'm joining you remotely. This meeting has been a long time in preparation. It was originally planned to be held in April 2020. However, COVID intervened, and it was then planned for last year, but had to be deferred again. So I'm particularly pleased that we are finally able to hold it now. It is particularly interesting and important to understand how our perspective on climate change has developed over several decades, how that has affected public policy, and how the latter has in turn posed new challenges for the climate science. The scope of today's meeting is broad, and so I hope there will be something of interest to everyone. You may also be able to reach a wider audience. Paul Simon, who writes the Weather Eye column in the Times, is joining us and plans to do a piece on the meeting for the Times. Finally, you will be able to ask questions of the speakers and comment in the panel discussion later this afternoon. Those online will be able to pose questions using the chat function. Our chair today will be Professor Chris Folland, who has also organised this meeting. Without further delay, I would like to invite Sir Brian Hoskins to introduce the subject of the day. Sir Brian.
Thank you very much, David, and get better, we hope, soon. Welcome, everyone. It's great to see you here. It feels very informal, but maybe there's millions out there online, so I better not be too informal. But thinking about this, what I should say here today, reminded me of my own journey through this. And the climate science itself has developed hugely in the last 60 years. That's not quite my research career, but nearly. I remember the first public talk I gave on climate change was in 1979 at the Clean Air Society in Scarborough. And it was a very different time then. First, the audience had no idea what I was talking about. There was no understanding that the climate was changing. And in fact, the mayor of Scarborough sounded very pleased to think there might be a couple of degrees warmer. And the other thing was really that we had no idea how we would deal with this problem in terms of particularly energy production. So a lot of things have changed now in terms of the understanding of the problem and the public awareness of the problem and the political awareness of the problem and some actions, as we'll hear later on. But the science has developed hugely as well. So Chris has put together this very nice program. It was his idea in the first place. And you'll hear these wonderful speakers later on taking us through this realm of the past climates and greenhouse gases and the perspective from the history of science, the historian of science, data, modeling, and the human impact, and science for policy, both in mitigation, adaptation, and finally, well, David was going to give, I think, the response of society. I don't know whether that's still happening. So I thought I'd give a few words on topics that may not be covered quite so much, particularly as they very much down my sort of line. And one of those, I think, which is essential to any projection for the future in climate, is actually an understanding of the climate system. And a huge part of that comes from the previous work in terms of over many hundreds of years of trying to understand the trade winds, the westerlies in middle latitudes, and those sorts of things, which generally by the 20th century was known as the general circulation of the atmosphere. And when I was starting my research in 1967, Lorentz produced this fantastic summary of the situation at that time, the understanding and the history, where it had all come from, of the general circulation of the atmosphere. So there's younger people listening. Do look back at Lorentz's book in 1967. It was fantastic. So he linking the motions of the atmosphere, such as the trade winds or the westerlies, to the heat sources and sinks, the momentum sources and sinks. But the but the emphasis being on the motions themselves and understanding that. So Lorenz talked about Halley, Hadley, and then in later years, in coming to the 20th century, we have Rossby and Charney and many others. Now in the UK, Jeffreys is one of the people who made a superb contribution in the early 20th century, where he's talked about the role of the eddies in maintaining the westerlies in middle latitudes, that the eddies, the mid-latitude weather systems, have tilted troughs, and that means they transfer momentum, and that is crucial in maintaining the westerlies. So Jeffreys was the first one to really say that. And then we have later on Eadie, who made superb contributions on the role of the eddies and the general circulation in general, and that went through a line of John Green, etc. So another thing that was very much in the UK was the publication in the Quarterly Journal of the Royal Meteorological Society by Norman Phillips of the first model, numerical model, really, of the general circulation, where he showed where if you impose simple sources and sinks of heat, then the eddies will actually develop those westerlies and the easterlies, etc. So that was a superb paper there that showed it was possible to describe the general circulation of the atmosphere, the climate, in a numerical model. And many people took on after that, and Joe Smagorinsky and co-workers, including Suki Manabe, who recently got the Nobel Prize, took off in the US. And in the UK, there was a lot of interest in this, both in the academic circles and in the UK Met Office. And in the UK Met Office, then George Corby took over the role of modelling the climate system, and that led through Met 20 and through to the Hadley Centre and the line there. But I also wanted to mention the university line that took off from there. People like Bob Pearce, D.R. Davies, John Green saw that it was necessary to collaborate in order to take part in this new world that was being developed. And there was a UK Universities Partnership, which is what I came back to the UK in 1971 to take part in, the UK Universities Atmospheric Modelling Group. And I just wanted to mention one of the postdocs there, David Andrews, who is a superb atmospheric dynamicist. He was one of the postdocs, and he was a lovely person. David actually died the week before, so I just wanted to remember him now. So we had the UK Universities Atmospheric Modelling Group, and that went through something called UGAMP. I won't even tell you what it stood for. And that led in a line through to NCAS Climate. So it was the NERC-funded research and the universities very much in partnership. Now, the relationship between those two lines, the UK universities and the Met Office, went through its ups and downs, I think we could say. But I think in the last 20 years, it's really been very much a partnership across the whole scene and the spectrum, from understanding the climate system through to really very active interaction with policymakers. And that's what we're hearing about today, this journey that we've taken there. And so I really think that it's necessary now, not just for me to continue, but to step back again to that wonderful program that Chris has put together here and to the other speakers. But have a good day, and we'll be back with a panel meeting at the end. Thank you.
Thank you, Brian. That was very, very good. We now go to the main speakers. I just want to say one or two words first of all. In the online version of this meeting, there's a full description, at least for most of the speakers, of their backgrounds. So I won't be mentioning that. You can read that online. The other thing I'm going to say is that for the speakers, the talks, including questions, are about 25 minutes. So perhaps about 20 minutes or just over for the talks. And I'll let you know if you getting close to removing any possibility of questions. Otherwise, I shan't say anything at all. So the first talk of the morning, which is going to give us a part of the wide perspective that we're trying to get from this meeting, is that the development of ideas about climate from 800,000 years ago to the present by Dr. Liz Thomas, who's a paleoclimatologist for the British Antarctic Survey. Liz.
Okay, good morning, everybody. And thank you very much for the invitation to come and join this meeting. And just as a side note, it is just so nice to actually be in a room with real people. I have, so many Zoom meetings where I think we're all getting quite sick of them. So thank you for actually coming today. So as I feel my role in this meeting is really to give us this longer term perspective so we can put some of the discussions that we'll probably build throughout the programme into a bit of context. And I've been given the task really of presenting the last 800,000 years of climate history as derived from the ice cores. But given that I've only got 20 minutes to do this in, I feel this may be a bit more of a gallop than a stroll through here, but I'll try and see if I can cover as much as possible. So I'm going to start really just by presenting, I'm sure most of you are going to be fairly familiar with this, so there will be a bit of old ground. But this is the really iconic ice core record from the Epica Dome Sea ice core, and it captures this 800,000 years of climate history. So I'm just showing you here, this is the stable water isotope record, but I'm presenting it here as the temperature anomaly. And this really captured the natural variability from cold glacial conditions and then to these warmer interglacial conditions. And this is part of the natural climate variability based on the Earth's position relative to the sun, which has these sort of very clear, distinct sort of 100,000 year cycles. And what this record was able to show us is that as we've moved through these transitions, we've got these very cold conditions, but actually there's evidence if you look at the record here. So we've got, just for kind of getting your bearing rings, I know I'm paleo, so we sometimes do things a bit backwards, but present is me, and we're going back in the past over in that direction. And so what you can see is that actually during these warm interglacials, there is evidence that previous warm periods were actually warmer than we have today, at least as captured in the ice core record that I'm showing. But I think the really important thing that really sort of stands out from the ice core, and the very unique thing that ice cores can actually do, is this combination of reconstructing the temperature and the climate and the composition of the greenhouse gases. So I'm overlaying here on top of the temperature proxy the concentration of CO2, and this is from a combination of ice cores from Antarctica. And what we can clearly see is that we've got this very very close relationship with the temperature and with carbon dioxide. And this is all part of the natural variability that's so important to explain and put this into context. Because back in the glacial, when we had on average concentrations up to maybe 200 parts per million, the Earth looked very different than it does today. So this is just a sort of snapshot schematic of what the Northern Hemisphere would have looked like during the last glacial period. And so we had these large ice sheets spanning across much of the Northern Hemisphere. We've got the Scandinavian and Laurentide ice sheet. And so during those conditions, the Earth was, a lot of this was under ice. And then it's as we change into the interglacial conditions when we get a big increase in CO2. And this is because the ice sheets have retreated. And I kind of think of this as the Earth's opportunity to breathe. It's lost this ice, sea levels have increased, and the biosphere can kick back in again. And that's why we have this very close mechanism. Now, CO2 obviously gets a whole lot of press for very good reason, but the other important greenhouse gas to remember, and that we're also able to reconstruct from the ice cores, is methane. And so arguably this is a more potent greenhouse gas, and we're able to reconstruct this at very high resolution through the ice cores. And again, this captures this same transition from low concentrations during the last ice ages, the glacial period, and then increasing to higher concentrations during these interglacial time periods. And this is again, this sort of kicking mechanism of the biosphere as the planet was warming and the ice sheets retreated. Now, given the experience of some of the speakers that we've got later on, I'm not going to go into too much detail about this sort of connection with the greenhouse gases and the climate, but I am just going to jump to the end, if you like, and this is kind of the key note, really, the key message and the context from the ice cores. So slightly shifted the axes here to fit this all on the plot. But you can see what we see over the last 800,000 years of these natural cycles. And then right up at the end here, we've got what we're seeing in present day. And for those keen-eyed among you, this is present day in Antarctica, not present day as recorded through the instrumental records. But what we can clearly say is that what we're experiencing, or what we've got, the concentration of greenhouse gases in the atmosphere today is significantly outside anything that we've seen before. And I think it's not just about the concentrations, it's not just about how much, it's about the speed of that transition. So the rate of change during the last 150 years is faster than anything we've seen. So one of the arguments being, well, we've seen these rapid transitions in the past, but even these switches from glacial to interglacials, I'll go into more detail later, they took several thousand years, whereas the changes that we're seeing of a similar and actually much larger magnitude are occurring over a matter of just decades. So again, just plotting the methane on here, because I think it's really important to kind of consider not just CO2 as the greenhouse gas here, but actually the changes in methane are even more abrupt. So what we're seeing in the present day atmosphere today are considerably higher than anything we've seen during any other warm period in the last 800,000 years. So now so this is just, sorry, this is a little bit of putting up here. I think one of the things I wanted to get across was that this is the bit that ice cores are so powerful in, that their ability to capture the public's imagination really, and really understand. If you can show somebody an ice core and show them the bubbles, and I wish I brought some, but if you can show someone the bubbles and they can hear them fizz and crackle, and you can tell them, take a deep breath in, that's the cleanest air you're ever going to breathe. It's such a powerful message. And I think that is where ice cores are so important in this sort of story and this history of climate, if you like. So these are just some of the examples from the recent lead up to the COP26, how we had huge sort of media engagement and also bridging across into the arts as well. So the little picture over there is a vial of air from 1760. And so this was really sort of demonstrating, this was the last little piece of air before the climate changed and the concentrations of carbon dioxide increased. So going back into our journey through time here, the other key thing I wanted to note was the sort of idea of this meeting really is sort of the history of climate. And so I think it's worth putting on here humans, where is our history? Where did we begin? And I find 800,000 years quite a staggering number, but it's even more so when you think actually, human species started developing more like 5 million years ago. And it was actually 1.8 million years ago that Homo erectus migrated out of Africa. So that's still, I find, quite a staggering concept. So through all of this, very natural but very large changes that I'm showing you, humans or human species were present. So just to kind of bring us forward and put a bit of context onto where we actually begin, we go through the different, known Homo species, Homo neanderthalis, which believe went up to about 30,000 years ago. But then it's really this last period up to about the last 200,000 years ago where Homo sapiens start to develop. And I've just put the little dots back there because I believe there is some evidence we were actually present back to about 300,000 years ago. So this, I think, is just so important as a concept, because if we're thinking about what our ancestors would have experienced in that time, this discussion about climate, we're saying maybe happened as recently as the sort of 70s. But actually, I think as a human species, we've probably been thinking about climate quite a lot, because these huge changes in climate would have made massive differences. And, that is how our population has expanded across the globe based on these big changes, opening up these sort of land pathways. So I guess the next part I'm going to move on to is just focusing on this bit, the human timescales, the last 200,000 years. So I'm going to move on to just the last glacial cycle. So again, I'm showing you the same figure that I just had, but just zoomed in, so the last glacial cycle. And the key things to note, as I mentioned, is that previous warm periods have been warmer than present. So just looking at the last interglacial, this is often used as a sort of analogy for potentially future climate change. And so it's a really important time period, and particularly there's a lot of ice core research around this time. But what you'll notice is that actually there's quite a lot of evidence that suggests during the peak of the last interglacial, about 128,000 years ago, temperatures were warmer than today. And globally, we believe this is about 0.8 of a degree. But the warming, it was interesting, was substantially greater at the poles. So very similar to what we're seeing at present. So moving forward in time, we're going now into the glacial. And so although you can see this transition from the last interglacial to the glacial conditions was a fairly gradual thing, what you can see is that actually there's a huge amount of variability within the glacial. So there's by no means this sort of switch from one stable state to the other. Within this, we've got this other background of natural climate cycles, which sort of form on about a 20 to 40,000 year cycle. And this is looking at the Antarctic ice core, and we can see these transitions that are known as Antarctic isotope maximum, and they've got this sort of almost symmetrical shape. But if we look at what's happening in Greenland, and this is really important because this is the only point at which the Greenland ice core records enter the story, as we only capture this last glacial cycle, what we can see for these transitions during the glacial is that they are much more extreme. And so looking at these jumps in here, these are now in the northern hemisphere known as Danskard-Erskine events. And what we see is these very abrupt warmings in the order of about 15 degrees that occurred over a matter of decades, and then this more gradual drop back down again into colder glacial conditions. And if you allow, I'm just going to take a slight detour into an event 38,000 years ago. And this is just a little pet favorite of mine because this is some work I did on my PhD. So just again, the figure I've flipped on the side, so you hopefully always know where we are in time. The second plot in here is just highlighting in yellow where I'm looking at. So what I wanted to do for this study was to try and understand what it was that was causing or driving these really abrupt changes. And importantly, also determine how abrupt were they? You know, how many years did it take? And this is where ice cores are fantastic because they can bring in a multitude of different proxies. So the figure that I'm showing on the far side over there is at the top, we've got the isotopes, exactly the same as I've just shown you. And we can see that we've got this transition into warmer conditions. Then the next record down is called deuterium excess, and this is capturing changes in the source region. So this is a secondary isotope tracer. Then the two figures that I've got in the middle, calcium in green and sodium in blue, these are telling us about changes in continental source regions, so about aridity in the mid-latitudes, dustiness basically. And then for the sea salts, it's telling you about storminess, but also about wind strength and atmospheric circulation. And at the bottom is telling you how much snow fell in each year. So this is whether it got wetter. So from these sort of studies, we're able to then start looking more into the mechanisms, you know, what happened and what occurred. And from the findings of this, which has then been repeated through lots of different Danskard-Erskine events now, is that actually we believe these are triggered by more of a low latitude change, which is then followed by the warming. So it's interesting to think that the mid latitudes are reacting first. Then we've got this warming that we see where we get warmer and wetter conditions. But I think what's quite interesting and stark is that this transition, this shift from source regions, from one source region to another, occurred in just a year. So these changes are very, very rapid. So back on our journey now, and we are approaching the deglaciation. So this is the time when we transitioned out of the last glacial and into the present. And this is seen, so we've got Greenland on the bottom here. Greenland starts to show this sort of warming, and as we reach the end of the glacial, considerably earlier than Antarctica. And actually, if you look at the Antarctic record, it's one of the most stable periods in the record there, from about 26,000 years ago to about 18,000 years ago. But what we've got in the middle of this deglaciation is this was punctuated by very abrupt climate changes. So we've got abrupt warmings, and then we've got this younger Dryas abrupt cooling. And this, for those of you who may be familiar, has been linked very closely to meltwater pulses. So the release, or sort of very large catastrophic release of fresh water from the remnants of the Laurentide ice sheet as they are retreating back, which then causes a slowdown in the meridional circulation. But these are all things that I think we're all fairly familiar with. And sometimes we kind of take it as given that these changes from ice cores are telling you about temperature. But actually, how accurate are these reconstructions? And is there more that can be done to better constrain this? You know, how it is quite important for us to understand how big and how large the natural variability was, especially in the context of future predictions. So it's important to remember isotopes are a fantastic record of past climate. I'm not saying they're not, but they are dependent on a huge number of factors. So not least surface temperatures, sea surface temperatures, changes in the sea ice, and important ones is changes in elevation. And these are often not taken into account in these earlier reconstructions. So now I'm going to take a slight deviation into some quite recent work, really, in an attempt to start to recalibrate this paleo proxy. So what I'm showing you here is a map of Antarctica, and we've got these 7 deep ice core sites plotted on top. And what we're looking at is the temperature change from the pre-industrial, so about 2,500 years ago, and the difference between the temperatures during the last interglacial, so 21,000 years ago. So what we can then see, these are reconstructions. And importantly, the difference of these reconstructions based on, rather than just the isotopes that I showed you, is that they're taking into account key firn processes. So these are the processes that take place within the snow. They've also been calibrated independently to different temperature proxies, so taking the temperature of the borehole. And so this is quite important because this is updated and improved our reconstructions. But clearly what you can see on the plot here is I'm overlaying the temperature change from these ice cores on top of what the model simulations would tell you the temperature change should be. And hopefully some of you can see that in the blues are a little bit subdued, but in West Antarctica, you can see that the ice core records suggest that there was a very big change between these periods, between the last interglacial and nearly present, in the order of about 10 degrees, whereas the models suggest it's a much smaller change. And so what we need to now do is try and understand, take advantage of all that information that the models provide us to try and better constrain the ice core reconstructions. So a key thing to take into account is the elevation. And so this is really important. During this big transition, and we showed the plots earlier, but focusing on the northern hemisphere ice sheets, during this big transition from glacial to interglacial, Antarctica also changed as well. And so it's a bit confusing on this figure because they've done the difference between present going backwards in time. But actually these browns on the map are actually indicating that during the last interglacial, when it was extremely cold, West Antarctica was higher. So the numbers look a little confused. But what this means is as we move from very cold conditions to warm, as expected, West Antarctica reduced its elevation as it lost mass, resulting in the sea level rise that we've seen in a range of other paleo proxies. So when we now take this into account, we can see that actually West Antarctica is changing quite dramatically during this time period, but hopefully you can also see that the ice cores from East Antarctica, the change in elevation was relatively small. So now we can take these into account and we can replot our data and rerun the simulations, but this time using a more realistic topography from the last glacial maximum. And what you can see is that we've now got a much greater a much better match between what the model simulation tells us and the ice cores. So this is really important because it's recalibrated the paleothermometer and shown us just sort of how important this is. There's also been quite a lot of studies based on very similar elevation changes during the last interglacial as well. So it's a really important area of research. So moving through in time, so I don't overrun, we've now reached the Holocene. And at first look, it looks like it was a relatively stable time during the Holocene, but I'm sure we're all familiar with the fact that it really wasn't. And these are because there were some very key rapid climate change events that occurred during the Holocene. So I'm just pointing out the 8.2 kiloyear event, and there are other known smaller events. And these are where the climate, or at least in the northern North Atlantic region, where temperatures dropped in the order of 6 degrees very rapidly. And so these are a number of different paleo records that capture this over quite a wide region. And in fact, there's also been a lot of debate about whether the 8.2 event is seen in Antarctica as well. And one of the key things for the 8.2 event is that it's been a really good example of where modelers and paleo can start to interact, because I believe for the modeling community, this is a fantastic case study. What triggered this rapid event? And so there's been lots of ideas proposed. And essentially, it's about freshwater input into the North Atlantic, which caused the slowdown of meridional circulation. And again, this is because we've still got the remnants of the Laurentide ice sheet sat over there on North America that then were able to release fresh water. So there's been a number of studies proposed. However, some of the things that the modelers were unable to do until quite recently is actually capture the speed and, importantly, the shape of the event. So this is again where ice cores have come in, because with an ice core, we can accurately date down to individual years what was happening. We can determine exactly how many years this event lasted for, how abrupt it was, how long lasting it was. So by annual layer counting, we're able to determine that there is this 160-year period where the climate did sort of cool. But within that, importantly, we've got this very abrupt transition, which I termed the central event, where we get the really extreme temperatures. And this was only a 70-year period. So this information then allows the modelers to take this into account and start looking at processes that are quicker And so some of the other ideas that have been proposed recently are things like the ice saddle collapse. So where we've got these two remnants together, it's this part in the middle that collapse causes this catastrophic flooding, which is a very strong pulse, but a short-lived one. And there we're able to then replicate in the models more the symmetry and the shape that we can capture in the ice cores. So now I've kind of reached the end of our 800,000 years, and we're into the present. And I think it's important. I know I was, really trying to provide the context of what natural climate variability, and that is a fantastic thing that ice cores can do. But actually, it's also worth noting we can also capture what's going on in the modern era and capture both the natural and anthropogenic changes. And for this, though, we have to step away from the comfort of the deep ice cores and now start moving into what other records we can get from Antarctica. And so I'm showing you here, this is a reconstruction of climate based on ice core stable water isotope records from across the Antarctic continent, but just looking now at the last 200 years. And one of the key things to note is that we've got some of these areas of red and orange on the map are showing these warming trends, but importantly, across the whole of East Antarctica, we're not picking up anything significant. And I'm just showing the time series in the blue over there as well. And this is because the East Antarctic ice cores receive such a small amount of snow accumulation that they're really insensitive to the kind of changes that we're seeing on the order of decadal scales. So they're fantastic at capturing these long, millennial scale changes, but they are not sensitive enough to capture what's been happening during the 20th century. So that's really important. But if we start looking at ice cores from other sites, West Antarctica particularly, and also coastal regions are really important, we can see that this warming trend is picked up in the ice core records, most notably in the Antarctic Peninsula, where we really can capture this warming trend during the last 50 years and put that into context and say this was actually part of a 100-year trend. Now, this is where I'm going to get a little bit controversial, and I've started talking about isotopes, and the traditionalists, isotopes are the best proxy for past surface temperature. But I am also going to propose another one that I think is as important, and that is actually the amount of snowfall. So it's how much snow fell each year is telling you a huge amount of information about a huge range of processes in terms of atmospheric circulation, changes in sea ice, changes in moisture source, but also ultimately temperature, because in a warmer world is a wetter world. So what I'm showing you here is a reconstruction based on 79 ice cores from across Antarctica from 1800 to 2010. And the dashed line is the annual, and then we've just got a running decadal mean through here, and comparing this to the modeled and observed surface mass balance in the red. Now, what we can see, unlike what we had from the collection of isotope records, is that actually here, the snow accumulation really is quite sensitive to this change. So we've got a very clear warming trend throughout this 200-year period, which accelerates quite dramatically during the latter part of the 20th century. And so what we propose is that potentially we shouldn't be relying just on stable water isotopes. We should be taking advantage of this other information that you can capture from the snowfall itself. And this is a paper I've done where we're working with the modeling community as a data model assimilation. So we're taking advantage of all of that fantastic physics that the climate models have and combining it with the temporal variability that we can capture from the ice cores. And what we've produced is these reconstructions. So the reconstructions shown on here have been compared then with temperature reconstructions from the climate models and also independent observational reconstructions. And at the top, we've got how well this compares. So how well does the reconstruction from ice cores using isotopes compare with the models? And you can see it's pretty good, 0.62. But actually, the number, if you just use the snowfall, is also pretty good, 0.51. But I think the key thing here is to note that it's much better if we can combine all of this information together and use both the snowfall and the isotopes in our reconstructions. But I'm just going to finish up with, I think, the final thing that I think is so important about actually measuring directly, just looking at the snowfall record, is because this tells you not only about the climate, that is obviously important, and temperatures, but I think the bit that we're all really concerned about is sea level. And this is where measuring the amount of snowfall is a direct indicator of what's happening with sea level. So again, I'm showing this time series. Here now I'm just focusing on the 20th century. And I'm showing it in terms of mass. So this is in gigatons. And what we've got is the total increase in snowfall in the black for the whole of the Antarctic ice sheet, and then separated out by the different regions. So you can see the East Antarctic here in the red, although it looks as if it hasn't had a very big change if you just looked at an individual record. But because East Antarctica is huge, if you combine all of this information together, this is actually where the majority of the increases in snowfall has occurred. And also just showing you then on the plot on the far side there, this is the exact same thing, but I'm showing it spatially. So if you look closely, you can see all the little yellow crosses. These are the ice cores. And then what we're showing on the map is areas where we've had more snow in the blue and areas where we've had less snow. So it's important to remember this isn't a homogeneous increase. There's a huge amount of variability, and this is what's really interesting and crosses right over with the understanding of atmospheric circulation and crosses paleoclimate with meteorology here. So we can see that the Antarctic Peninsula is obviously the area that's sort of dominating with this big increase in snowfall. But I think the final and most important outcome of this research is how you can then convert this to changes in sea level. And what we found is that the increase in snowfall during the 20th century, in the order of about 272 gigatons, was enough to mitigate 20th century sea level rise by 10 millimeters. So that's quite an important result and an important finding. And it's worth noting that actually up until a few years ago, the general consensus and assumption was that Antarctic snowfall has not changed. So this is quite a big finding. This really does sort of change our perception of the importance of snowfall and the importance of Antarctica. So we're all aware that Antarctica has been losing mass, but here we're saying actually it's also gaining mass. And the important thing is now we want to look to the future. And this is a study from last year. We're actually taking this forward using the reconstructions and simulations from the CMIX-6 models. And what we can see is we've got surface temperature on the left, and then the SMB, which is surface mass balance, the same snowfall or snow accumulation. So clearly, when we have these greater warming scenarios, we've got a bigger increase in snowfall that's going to fall on Antarctica. And actually, in this study, they concluded that in the future, leading towards the end of the 21st century, the amount of snowfall on Antarctica is going to be enough to actually counter the mass loss from melting. So this is a really important result. So just to kind of conclude how ice cores have actually shaped our history, I think it's key to note that ice cores are really valuable in capturing these natural cycles, these millennial scale changes in greenhouse gases, the glacial to interglacial transitions, but also capturing these much smaller, more abrupt climate change events and really determining the processes involved and the speed and rate at which the climate can change. But I also want to say that ice cores still can be very useful in this modern era as well, and capturing these anthropogenic changes, both in temperature and also in greenhouse gases. And with that, I will finish. Thank you.
That was a great talk. Thank you very much. One question I had was that EPICA and NGRIP were, I don't know, 10, 15 years ago. So what has been the emphasis in ice core science in that? Has it been taking additional cores or additional analyses or all of the above?
All of the above. So that's a good question. So in one way, the easy answer is to say, so yes, that those cores were drilled quite a long time ago. And actually that's why as the ice core community, the international community are actually at present hunting for the next deep core. So the ambition is that we might extend back beyond 1 million years. But that's in terms of just collecting more ice. But it's important to note that what we've been doing with the existing ice is extracting a huge amount of information. And quite key for me is it's developing new proxies. You know, there's a huge amount of information in an ice core. I was just presenting, tip of the iceberg there, the really traditional things. But, there's biology that we're sort of discovering and learning about that's telling us about changes in circulation. There's new ways of reconstructing sea ice. And there's, as the analytical capabilities have increased just in the last few years, what we can see and what levels and concentrations in an ice core is improving. So yeah, we've not been just sort of sat on our hills, just riding this one at all. But also importantly, it's now, I'm a bit biased myself, but my own interest is moving away from the deeper cores and looking more at the changes around the more coastal regions and actually targeting these really dynamic regions. And what we don't yet have is a really good high-resolution long-term record of changes in the Antarctic Peninsula. All of the records I've drilled only go back about 300 to 400 years. So there's still an awful lot more that we don't know, and we're kind of building on.
Thank you. Great.
Thank you.
Hello, thank you very much. Just at the end, you talked about increasing snowfall, balancing, melting. But what about dynamical changes? Could you put that into a bit of context with, faster glacial flow, etc.?
Yeah, so it is really interesting. And this is, so I'm involved in one of the SCAR, so a Scientific Committee on Antarctic Research Groups, looking at these instabilities and thresholds, because it is really important. So that was just a model that's saying, what does the model think that snowfall is going to do in the future versus what is temperature going to do in the future? And the important thing is that although I think these models are fantastic, they are still a model. And there's still a lot more information we need to put in. And actually, it's those dynamical processes you were just saying, what's actually happening to the glaciers, the advancing, retreating. And there's a lot of arguments as well that have not fully been explored. But one of the things that happens if you start to increase the mass on the top of a glacier, so you start dumping more snow on top of it, it will actually have an accelerating effect. So a lot of these feedbacks haven't been taken into account because they're based on climate models rather than an ice sheet model. So I think that's definitely a really interesting area we next need to move into. What are these dynamical processes? I can answer it again if you like.
Can you say any more about sea level rise in the future in terms of looking at the past interglacials?
Yeah, so one of the reasons I said that the previous interglacials, particularly the last interglacial, is so important is because I think we believe it was about sea levels were about 6 meters higher. But there's still quite a bit of mismatch between what the paleo archives indicate the sea level change was and what we believe Antarctica could have potentially lost. And I think this is because still as yet, it's these dynamical processes that we haven't quite understood. So there's an expectation that this increase in sea level must have come from Antarctica, because where else would it have come from? But we still haven't been able to match that up with actually what the observations from around Antarctica have told us. So we have a project that we're working on, an EU-funded project, where we drilled an ice core at a place called Skytrain. And the intention of that core is to really focus on these last interglacial changes, looking at whether the West Antarctic ice sheet really did collapse or whether it was still present during the last interglacial, because that's a key number that we need to put into our calculations. And if we can't understand what happened in the past, then how can we really expect the models to predict what's going to happen in the future?
Thank you. I think we've got time for one more question.
Thank you. I was fascinated to see the sort of the freshwater aspect that you're showing. Quite a short timescale event, which seems to have a big impact. I guess there's quite a lot of internal variability in some event like that. And does that sort of put some limit on how well our climate simulations will be able to match the reconstructions?
Yeah, so that was one, I guess maybe you're talking about particularly like the 8.2 event and the Younger Dryas and things. Yeah, so this is where, it's the advantage of bringing together lots of different paleoclimate records, because they can tell you more widespread how the climate is responding and the sort of potentially leads and lags as to where it reached in different areas. And the theories about this outburst flooding, I think it kind of confused the modelers for quite a long time, because the amount of water that was suggested from the paleo records that was actually released, just wasn't enough to create these really sharp transitions. It created more of a very, all the models seem to come up with something quite smooth. But I think now that we're able to get down into the detail, how quick and how fast, that's where this idea of the saddle collapse came in as this potential for, that these sort of outburst flooding. So essentially the ice is still there, these remnants, but we've got water behind it. And that actually those changes can occur on very short timescales. So I think it was important in showing it's not the amount of water that goes in. So these, I think they call them sort of hosing experiments, where you just put fresh water on a grid cell. It's about exactly where they entered into the circulation and exactly how fast. And so those are really, really important. So you couldn't replicate the same thing if you just hosed it over a long time period. It has to be a pulse. I hope I've kind of answered a bit your question.
Thank you.
Okay, thanks very much.
You're welcome.
Okay, so we now come on to the next talk, where we moved from what was natural climate variability, though notice the greenhouse effect was part of the ice age fluctuations, to the development of ideas about greenhouse forcing of the climate. Joanna Haig, who is Emeritus Professor at Imperial College.
Thanks very much, and thanks to Liz for that really fascinating talk on essentially current science and what we understand about the past climate. Just making sure I'm going to not run out of time. So I'm talking about the history of the science rather than the science, the history of the climate, and particularly understanding of the greenhouse effect. And just in case anybody's not certain, I'm sure you all are, but I'll quickly review what is the greenhouse effect. And this is, we understand a process which ensures that the surface of the Earth is warmer than it would be were the atmosphere not exist. And what happens is the sun's radiation, a lot of it gets through the atmosphere and warms the surface gets warm, emits heat upwards, but the atmosphere, while it transmits a lot of the solar radiation, absorbs nearly all of the infrared heat radiation and emits it downwards and upwards, and the downwards component warms the surface, and this is now become known as the greenhouse effect. So what am I going to be talking about today? Said that. This is a very grand slide, but it's just a challenge to me that all the things that I could talk about, which I probably won't do, but this is, the topic. So who did what, where, when, and why? And they're coming at it from all angles, of course. Fundamental physics ideas, theories, hypotheses, do these things explain observations? The paleo context is what some people were working on. And then we've got all the ways of going about studying the greenhouse effect. We have laboratory experiments, measurements in situ in the atmosphere. We've got radiative transfer theory, all sorts of calculations and insights into the science. And finally, how that all fits into the whole climate science context, climate models and climate change. And so when I talk to undergraduates about why it's a nice or interesting thing to be doing, working in atmospheric and climate science, I say, look, all this stuff, all these things you can do, such a wide range of science, and you're working on something that's useful. Why not do it? Oh, yeah. So going back rather a long time now, this is Edmé Mariotte. Now, he's not working on the atmosphere at all. He's working on the physics of materials. But it's quite interesting to note that back in 1681, he noticed that certain materials, and he was talking about glass here, that sunlight energy can get through, but heat from candles and other sources does not. So he's identifying the fact that certain materials have different properties at different wavelengths of radiation. Of course, this idea is, although he wasn't talking about what we call the greenhouse effect, this idea is fundamental to understanding of our atmospheric greenhouse effect. Moving on 100 years or more, we have Joseph Fourier, who many of you will have heard of in the context of Fourier transforms and mathematics, working in France, but he also worked on physics, and this is his theory and analysis of heat. And he calculated the amount of energy that could be absorbed from the sun and the amount of heat energy that must be going out, and working out what the surface temperature of the Earth should be to manifest that balance. And of course, what he found was that their surface temperature should be much colder than the measurements. So he identified the fact that something was going on to make the surface warm, and perhaps that the atmosphere was acting as an insulator. So sometimes he's cited as the sort of first person to understand the greenhouse effect. He did at that level. I mean, this is not to dismiss his contribution, but he didn't understand about the radiation being transferred between different layers of the atmosphere or coming back to the surface and that sort of thing. So he made a mark in the sand, but I wouldn't say that was the first understanding of the greenhouse effect. Have we moved a bit further forward, also to another French scientist? Now we have Claude Pouillet. I'm sorry, this is a bit faint. Is it possible to reduce the lighting at all? I know it's the sun. Is it the sun or is it the lights? Oh, okay. This paper is on solar heat and also the properties of the atmosphere in transmitting and absorbing the solar radiation. And he was the first one actually to include emission of heat radiation by the atmosphere up and down, including back to the surface. And he understood that water vapour and carbon dioxide in the atmosphere trap infrared radiation, thus warming the Earth, and he noted thus supporting the possibility for life. So I would say that was probably the first paper talking about the greenhouse effect as we understand it today. Then I was going to say about him, he was quite interesting because he lost his job because he didn't support Emperor Napoleon. He didn't support the imperialist attitudes of the government, so he lost his job. So he was a good person as well, in my opinion. Now, going on to some laboratory measurements, this is Eunice Foote, who was an amateur scientist in the United States. And this is her paper on circumstances affecting the heat of the sun's rays. I read to the American Association in 1856. And she's talking about understanding what affects the heating of the atmosphere. Now, she's understanding that when there's carbon dioxide in the air, it absorbs more solar radiation. And then she argues that more CO2 will therefore warm the atmosphere. Now, of course, that's all correct. It's not actually the greenhouse effect, because she's only talking about really solar radiation, which is a small component of the energy budget, not the infrared radiation that we know is causing the greenhouse effect. But this is, again, making a mark in the stand for the science that she was putting forward, that atmospheric gases were causing the atmosphere to be warmer than it would be were they not there. So moving forward to John Tyndall, who you will all have heard of, and his famous paper read to the Royal Society in 1860. I can't remember what it is, and I can't read the thing because it's too faint. Thank you, Brian. 1861. He had got a famous paper that came out in 1870 something, but this is really the original one. He's done all these laboratory experiments understanding both the absorption and the emission of radiation by atmospheric gases. And this is one piece of kit. I'm not going to use the pointer because people online can't see the pointer. He's got a cube. The cube on the left there is containing hot water, and it's got a thermometer in the top that's measuring the temperature. And then there's this thing in the middle which has got the two cones pointing out, and that's measuring or taking in infrared radiation from both sides, one side from the cube and the other side from a source of gas. And in the middle, he's got a thermopile, which is looking at the difference in temperatures and producing a current in the galvanometer, which you can't see. On the right-hand side, you've got something that's called an argon sphere, which is warming the air, and you can see that simulation of hot air rising there. And around the argon sphere is a sort of circle with lots of little holes in, and you can squirt different gases, and that's what the pipe is coming in from the front, so that different gases go into that rising air. So the point is that you, first of all, you don't have your gases, you just have the rising air, and you adjust your galvanometer settings such that it's equal from the right-hand side and the left-hand side, so that you've got a balance. Then you introduce the gases, and you can see what effect they have, and a huge effect that he wasn't expecting. He was looking at, is it ethanol? Ethylene? Some horrible gas anyway. And he noted that a gas that was completely transparent in the visible could have this amazing emitting effect. And then he went on to study all sorts of other gases, including water vapour and what he calls carbonic acid, which we call carbon dioxide in context. So this is the radiation emitted by different gases. And then we have this other set of kit, which is he's studying the absorption of radiation. This is more complicated, but it's fundamentally doing the same thing. So you can see we've got the two cones up there attached to the galvanometer down the front. We've got the compensating cube. Then we've got a long tube, horizontal tube there, which is containing the gas to be studied. And the gases are coming out of this tank bottom left, passing through that wiggly array of pipes. In those pipes, there are various absorbing materials that can, if necessary, remove water vapor and carbon dioxide and other things to clean the air that's going to contain the gas which is being squirted in from the different sources. And then on the right, we've got a heat source. We've also got a vacuum pump that can suck the air out of the tube to start with, and then you put the gas of interest in there. And so what you're looking at now is the signal coming from the gas in the tube. So you're measuring the emission of the gas rather than its absorption. So this is a fundamental experiment which is providing the information that really turned greenhouse effect understanding really in the right direction, because it is showing that carbon dioxide and water vapor is having an effect. So I think I'll leave it there. If you can read that text down, this is him saying about his thoughts about why he was doing the experiment. So putting this into sort of geological context, so around the same time, end of the 19th century, there was a lot of geological scientists trying to understand about time series, rather wonderfully, like Liz has already explained, on the probability of secular changes in the atmosphere's carbonic acid concentration. So how was carbon dioxide changing in the past? And he's talking in the context of industrial contributions to the atmosphere. And he's saying that the amount that's put into the atmosphere by industry would create about 1,000th part of the CO2 at that time. And considering that this is going up, it might compensate for the CO2 that's lost in creating silicates. So this is on a very, very long geological timescale. But this is, of course, the whole carbon cycle as it's now understood, but the very slow carbon cycle. So he gave a talk, I can't remember where that talk was, but in 1894. And in the audience was Svante Arrhenius. And a discussion after Hogbone's talk was with whether these amounts of carbon dioxide could actually affect the temperature. And so Svante Arrhenius took that idea away and he really developed it. And this paper in 1896 on the influence of carbonic acid in the air upon the temperature of the ground. So he is credited by being the first person who really showed that the greenhouse effect would work, or was working. He used infrared observations of radiation coming from the moon that other people had got, and he used those to deduce the atmospheric absorption coefficients of water and carbon dioxide. So he's really getting into the guts of the physics. And he derived a relationship, a sort of logarithmic relationship between absorber amount and surface temperature. And he included in his calculations the effect of water vapor and ice feedback. So it wasn't just a direct radiative effect, it was including the feedback. So he really had getting into the guts of it. Now, I'm sorry, you won't be able to see this, but this is a section of Svante Arrhenius's results. And he's showing for different carbonic acid amounts. You see it says 0.67, 1.5. This is times the current concentrations. And he's doing the temperature changes at the ground as a function of latitude. So the red ones I've outlined there is the changes in response to a doubling of carbon dioxide on the surface temperature. And you can see it's more at high latitudes than at the equator, going between about 5 degrees and 6 degrees. So pretty impressive, given he hadn't really got any computers or anything to do it, and the properties of the gases and things weren't really very well known. So very impressive. And then he concluded that a 40% increase in atmospheric carbon dioxide would trigger the interglacial period. So he was thinking that was a very strong link between the CO2 and the ice glacial periods. He also predicted, as we've just seen, that the doubling of atmospheric CO2 would increase global average surface temperature by 5 to 6 degrees. So back to the geological timescales. This is then putting that into the context of the geology and in the carbon cycle. When the temperature is rising after a glacial episode, the ocean gives forth its carbon dioxide, understanding the temperature dependence of the concentrations of CO2 in the oceans at an increased rate, thereby accelerating the amelioration of climate. And I think Liz has disappeared, but she was perhaps say this is a fairly good representation of what we understand now about the glacial periods. So that's back in 1899. I included this paper by Niels Gustav Ekholm, partly because he says nice things about the Metsoc. This is presented to the Metsoc at its jubilee in 1900, a humble expression of homage and gratitude by the author, I should say the same. He didn't actually say anything in the paper very new from what I just talked about in the geological timescales, but he is credited with being the first person to actually say that the atmosphere may act like the glass of a greenhouse, letting through light rays of the sun and trapping the infrared, which was where the idea of the greenhouse effect name has come from. Rather unfortunate, because greenhouses don't actually keep the contents warm by doing that, but just by trapping the hot air. Never mind, that's just in terms of the history of the greenhouse effect, that's where the name came from. And then we come on to Guy Stewart Callender, who's an amazing person. He wasn't an academic physicist, he was a heat engineer. But his dad was head of the Imperial Physics Department, so I credit Imperial College with producing Callender. And what he did was he looked at a whole load of data from across the world on surface temperature records. And this is one of his plots, different parts of the globe, the temperature. He's collated different stations' data, and you can see the time scale at the bottom there, going from 1890 to 1920. And then we've got the Earth annual departures at the bottom, and you see the scale is plus or minus 0.2 of a degree, and this is Celsius. This is an extraordinary achievement to assimilate all that data and put it in here. And I just wanted to show how it's even better by trying to compare it. This is our of course, current assessment of global surface temperature rise. This is very poor graphics, but what I've tried to do without doing it properly and numerically is just to expand Callender's plot so that it's got the right horizontal scale, the right vertical scale, and you can compare the curve below and the curve above. And just by eye, you can see he's doing rather well. He's got the flat bit at the beginning and the rise at the end, and some of the big lumps are in the right places. So I think, just to say he was doing a rather excellent job. So these are some of his results. And he's talking about the changes in CO2. And this is, he's running a carbon budget model. He understands, again, about the absorption into the oceans. He's putting timescales on the mixing into the deep oceans and different carbon budget components. And so he's predicting what the carbon dioxide content will be and what the surface temperature will be. So if you look at the mean PCO2 there, the 20th century says 2.92. This is 292 parts per million as we understand it. So that's pretty correct. Then he's got it going up to 330 by the 21st century and 360. Unfortunately, he's well under there. He's also got the temperature rise that he calculated due to those CO2 increases. And interestingly, polar displacement of climate zones. So he understands that the impact is not just directly on temperature, but also on all the weather that goes with the different climate zones. But two issues remained with the science. One had been going on for a very long time. So I see this paper by Knut Angstrom in 1900 said that CO2 in the atmosphere wouldn't have an effect for two reasons. One, because its spectral absorption overlapped that of water vapour, so it couldn't do anything. It was so much more effective water vapour. And secondly, that the CO2 absorption is already saturated, so adding any more CO2 into the atmosphere couldn't have any additional effect. And this idea permeated all the way through. In fact, there is even some papers recently from the climate skeptics group trying to revitalise this argument. It's not right. We'll go into it in a minute. But and the other thing was actually the components of the carbon budget. I've already introduced various people trying to make estimates of the carbon budget. And of course, it's very important if you're going to relate CO2 amount in the atmosphere from human influence to temperature, as what that budget is, how much of the human CO2 stays there, and how much of it goes into different sinks like the oceans, like the biosphere. And so there's a lot of work being done on that. And in the 50s, the suggestion was that most of it was absorbed by the oceans, and so that actually it couldn't stay in the atmosphere, and so that it couldn't be having an effect. That's an important paper by Revalancius, except that I understand, I haven't seen this, but if you go into an archived version of that paper, there's something stuck on top that's changing the conclusions. Oh, actually, we got that wrong. It's stuck on with sellotape. Because Seuss did actually do some more work on this, and he understood that the ocean circulation was too slow to do what was necessary. That was one side of things, and the other side of things that he understood that there was, he could estimate that the carbon in tree rings isotopes was coming from fossil fuels. That was two important contributions that he made. And then, of course, in the late 1950s, we got the initiation of this wonderful series of measurements of carbon dioxide in the atmosphere that I've just reproduced over there, showing the CO2 rise. And we now know that that's coming from human effects. So relating in a more scientific way the carbon from the carbon budget, from the anthropogenic sources to the temperature, we have Gilbert Plass. He did all sorts of things, but he was very good on atmospheric radiation. And so he's done 1D profile radiative transfer calculations using more detailed spectra of water vapor and carbon dioxide, and including various important physical effects like the pressure broadening of the spectral lines, which affects how much absorption is taking place. And he showed very clearly that the absorption is not saturated, mainly because you get the wings of the CO2 15 micron band, which is the most important one for climate, just not getting saturated. The more CO2, it just gets a little bit higher, and the integrated effect is that your absorption goes up in a logarithmic way as integrated across the spectrum, not linearly, but it means that the CO2 is nowhere near absorbed now and won't be for a long time. So that argument's out the windows. And then he also did a carbon budget sort of estimates, and he's considering the rate of increase of fossil carbon and the slow uptake in the ocean. And he estimated CO2 in 2000 will be 30% higher than 1900. So that was a pretty good result, but he was a bit lucky because he'd, I forget which way around it was, he'd underestimated the human emissions and he'd underestimated the ocean absorption. So two things that compensated to give him the right result. But anyway. And then he says that if at the present rate of increase, the CO2 in the atmosphere will raise the Earth's temperature by 1.5 degrees Fahrenheit every 100 years for centuries to come. If man's industrial growth continues, the Earth's climate will continue to grow warmer. So that is another very prescient remark. So I've got something on climate models, but I know Matt's going to talk about climate models, and I'm not quite sure how. Am I short of time? Yes. Okay. So I'll skip the much of the climate model stuff. I just love this picture. When I was doing my DPhil, this is just my iconic picture. It's showing the heating rates in the atmosphere, the troposphere and stratosphere due to different gases. Anyway, right, carry on. And then we've got these papers by Manabe and Strickler, Manabe and Weatherald, looking at what the temperature response to CO2 increase would be. This Manabe and Strickler and 1D calculation, the Manabe and Weatherald with the fixed relative humidity. So he's taking water vapor feedback into account. And this is their temperature response on the right for latitude height. Oh, then I've got something on climate sensitivity. Perhaps I better just stop. Shall I? Do you want something climate sensitivity? So this is okay. So this is all to do with how much the surface temperature increases in response to an amount of carbon dioxide in equilibrium, which would be a very long time in the future. But this is called the equilibrium climate sensitivity, and it's a sort of key number in understanding how important CO2 is to climate change. Now, if you just work out a simple black body calculation, you get double CO2 will give you a surface temperature increase of 1 degree, but that doesn't take into account things like water vapor feedback, which I've already mentioned, the effects of clouds and sea ice, albedo, and also on a longer time scale, land ice and stores in carbon stores. And these all depend on location, the background climate state, and all sorts of other things. So we've got a series of papers. This was the US National Academy of Sciences report in 1979, estimating that the most probable global warming for doubling of CO2 to be near 3 degrees, the probable error of plus or minus 1.5 degrees. And that was based largely on those climate models that I've just introduced. And this is just a slide showing estimates of equilibrium climate sensitivity. I put PLAS in there, although he didn't really talk about it like that, and he hadn't got the full things. But you see that over the decades, it really hasn't changed at all. And the only thing that's happened in the most recent IPCC report, AR6, is that the likely range has narrowed. And they've gone around it, this last report, in a slightly different way by not just using climate models to assess the effect, but actually rather the opposite. They're not using climate models directly at all, using what you might call emerging constraints, or how it behaves from the models, but also other processes as well. So I'll leave it there. Yeah.
More about the history of CO2, how it was interpreted, than I thought it actually existed. So
Oh, thank you.
Tom, 2 questions. We'll go a little bit into the lunch hour. I think that's all right, because it's we're having lunch here, thanks to the society, so we don't have to worry too much about having to pull out. So a couple of questions, please.
If Keith wants to ask a question about the greenhouse effect, he can answer it himself.
Thanks. That was great. One of the interesting things that's puzzled me about Tyndall's work is it didn't produce a spectra of CO2, and it seems he had the technology to do so. I mean, and it was only in the 1890s, I think, that Rubens and Askinas in Germany produced the first spectra of CO2 and water vapor. And the thing they found was that rock salt, which is a filter of infrared radiation, is also dispersive. And it's always puzzled me whether Tyndall knew that and didn't exploit it, or didn't know that. But
I think he certainly didn't know about that, because some of the screens he has are of rock salt.
Pardon, say again?
Some of the screens in his equipment are of rock salt.
Well, that's my point.
So, I mean, he presumably didn't know about that having an effect.
Yeah, that's right. So he didn't know about the dispersive one, but it was a rock salt that Rubens and Askinas used 20 years ago to produce these beautiful spectra showing CO2 absorbing in 15 microns. And in many ways, that was a missing link to, if you will, all the way through to Manabe and people being able to use measurements to put into their
measurements
models.
by Birch as well.
Yeah, that's right. But I think that was the first time that Rubens paper was the first paper to actually produce a spectra, which was quite astonishing.
Tyndall must have known about spectra in general.
Yeah.
But clearly his apparatus wasn't doing that. It was just taking in any heat, infrared radiation that was coming in and warming the thermoplanes.
Yeah, that's right. Yeah, so it's interesting. Yeah, so thanks very much.
One more question.
So, not as in-depth a question as Keith's, I think, but given that greenhouses don't work by way of the greenhouse effect, I wonder what we should call it. I.e. the greenhouse effect, not greenhouses.
Atmospheric blanket? Anybody? Yes, it's unfortunate that it's stuck, but I think if we started saying it wasn't that now, particularly skeptics would find some argument to say that we were going back on what we said before, etc., etc. So, yeah.
Okay, thanks so much, John. And we now go on to the last talk before lunch from Sarah Dry, who is a historian of climate and climate change linked to the Science Museum, and she's going to talk about the history of in historical science, how climate science became a science of change.
Thanks. It's great to be here. I don't know if I'm the cat among the pigeons or the pigeon among the cats, but I'm grateful for the chance to speak to you in my capacity as a historian of science, and also a bit nervous to talk about a subject about which many of you are much more expert than I. But I hope my perspective on what it means to talk about climate and history is a useful one to bring to this topic. As we've already heard, there's many different ways of thinking about the relationship between climate and history. And in many senses, climate scientists are historians par excellence, and humble, regular old historians, we can never hope to compete with the spans of time with which climate scientists cope. But we have other methods and other things to offer. So I hope I can offer in my talk some useful considerations of what it means for us to talk about climate science as historical, and more generally on the changing nature of the relationship between how we think about climate and history, how we think about climate science and history, and of course, how we think about the relationship between climate scientists and historians. And as you'll see, and as I noticed as I was preparing this talk, I'm quite slippery in my use of terminology. So, historical, temporal, dynamical comes up. I'm happy to be pressed on that afterwards. I think that's part of the challenge of the subject, is sorting out different modes of thinking through time. So if that's all you take away from this, I'll be happy to have drawn attention to the ways in which our thinking about what it means to describe change over time can be distinctive. And I think, having seen already a bit of the paleoscience perspective, heard a little bit about models and theoretical perspective, we already are feeling some of the texture of that. So, let's see, is this going to go the right way? Yeah. So this is just a little roadmap, which I hope I'll follow. I'm going to just briefly describe the main features of the shift that I've described from a kind of which has its origins in the 19th century and becomes dominant or hegemonic, we might say, in the post-war period, from thinking about climate in geographical to dynamical terms. And after I've done so, I then want to sort of trouble my neat narrative and show, as historians like to do, that things are never so simple as we want them to be, and that while it's certainly the case that a physics-based approach to climate that relies heavily, though not exclusively, on computer models to generate experimental studies of climate dynamics over time has become dominant and remains so, there are many other important strands of the history that deserve our attention. I mean, why do they deserve our attention? I'm preaching to the choir here, but I think there's a couple of different reasons. I mean, not least they enrich and deepen our understanding of the past. And by the past here, I mean the past of the history of the study, the history of the science. That's a worthy goal in its own right. I think they also remind us today just how multidisciplinary climate science has been and remains. And sometimes those traces, I think, are elided. Perhaps, again, in this context, the differences are all too familiar to you. But I think certainly in the public sphere, that multidisciplinary nature and therefore history of climate science is often lost. And it may account for some of the problems of communication and translation that occur. And I think these histories can also serve as a kind of imaginative material for us to think about moving forward, a guide for the future. What are potentially alternative methods or relationships to figure our histories of climate? And this, in a way, I think, without getting too grandiose, there's nothing more important for us going forward than understanding the relationship of human history and climate history in the past and in the future, if I can put it that way. So my final point here is, why does this matter? Well, what are the ethical, the moral, the political, the social, and the cultural ramifications of all of the ways in which climate is historical. Why does it matter that scientists like you and others think about climate and history, or climate and time, or climate and change in the way that they do? So in order to understand a shift from one way of thinking about climate to another, we have to start with what came first. Of course, it's a kind of banality to say that humans have, as Liz already mentioned, one way or another, always concerned themselves with climate and always studied climate. I'm only going to go back to the relatively recent eye blink of human written history here, and to Alexander von Humboldt, the celebrated German explorer, naturalist, and geographer. And I'm especially interested here in Humboldt's concern with the unity of nature. I've put this sort of slightly playful doubled image of Humboldt up here to just indicate that he still remains a quite resonant cultural icon, another way in which we might continue to use the past as well as learn from it. So what's important about Humboldt? Well, many things, but what I want to say is that for Humboldt, the variation of the natural world was a product of the interaction of myriad universal physical forces. And these forces included those which affected climate. And what was climate was for Humboldt, this is a very brief definition, quote, all changes to the atmosphere which noticeably affect the human organs, including things like temperature, humidity, pressure, wind speed, and wind direction. And note that for Humboldt, climate was understood in terms of its differing impact on humans living in different regions of the globe. Climate was always understood in relation to human habitation, human lives. And it was part of the wonder, but also the order of nature that Humboldt sought to reveal, that the underlying consistency of these forces, the relationship between temperature and pressure, for example, gave rise to the complex and varied climates of the Earth. So on the one hand, we have universal forces, and on the other hand, we have this amazing climatological variation. So by describing and delineating these zones, these climatic zones, with using precision instrumentation and producing detailed maps like this one, Humboldt aimed to show that there was an order to nature, and importantly, that that order was stable. The uniformity of physical laws meant climatic zones, for example, could be reliably described and would not change. So Humboldt's vision, in this sense, was both global and it was specific, providing a framework for diverse climates to be mapped and related to each other. His development of the concept of isotherms, based on average measurements of daily minimum and maximum temperatures, further enabled this global mapping of climate features, which were understood to remain relatively stable over time. So later in the 19th century, Humboldt's work was adapted and extended by climatologists such as these men: Julius von Hahn, director of the Central Office for Meteorology and Geomagnetism in Vienna, and Vladimir Köppen, director of the German Marine Observatory in Hamburg. They transformed Humboldt's climatology into an institutionally robust and nationally important science, based on the collection and collation of extensive meteorological data gathered from around the world. In other words, climatology became an imperial science in the hands of these men. Their vision of the aims of climatology in this sense diverged from Humboldt's. They were less interested in uncovering the complex interrelationships between living creatures and their environments, and more in establishing a typology or geography of fixed climatic zones, which could be defined on the basis of meteorological averages. Hahn's 1883 Handbook of Climatology became the locus classicus of what came to be called the averaging climatology. That's my painful pun here. And while Köppen and Hahn promoted this so-called averaging climatology as having enormous practical benefits in helping nations and empires understand both the nature and the value of their territorial possessions, and how they might be exploited, but their theoretical ambitions remained limited. According to Hahn, climatology was, quote, but a part of meteorology in the broadest sense, and most specifically, it was the purely descriptive arm of meteorology. For Köppen, in climatology, quote, theories step back. the ordered collection of facts is the prevailing goal. For the time being, then, the theoretical ambitions of meteorology were best left to others, namely Wilhelm Bjerknes, who was the leader of an ambitious school of meteorology based in Bergen, Norway. And in 1904, Bjerknes had written a famously ambitious and influential paper I have a feeling many of you are familiar with, making the case for a solution to the problem of weather prediction using partial differential equations describing atmospheric and thermal movements. Solving these equations would, in theory, argued Bjerknes, allow scientists to describe and therefore to predict the changing states of the atmosphere, what Bjerknes hazarded to call dynamical meteorology. So as long as Bjerknes's equations were not able to be solved directly, their utility remained limited. Bjerknes had laid down what was essentially a token of intent for the aspirations of meteorologists, but the fulfillment of a vision of truly dynamical meteorology lay in the future, one that could produce, for example, practical forecasts that could be used in time, that could be generated in time to be useful. Other things happened to help this shift from this geographical vision of climate that I've described into a more temporal frame, not least the growing availability of observations. So from sort of, let's say 1880 through to the 1940s, there's this massive increase in data on the upper air, which had really previously been more or less unavailable to climatologists seeking to understand atmospheric circulation. So you get balloons, kites. By the 1930s, you get radiosondes that can transmit data from up to 15 kilometers, apparently, in the atmosphere, down to ground-based receivers. And following the war, a German climatologist, Hermann Flohn, and Swedish meteorologist, Sverre Petersen, used this newly available data to develop a new theory of planetary circulation. And in their work, Petersen and Flohn were building on the ambitions for meteorology that Bjerknes had raised earlier. With the addition of this global scale observational data, they made the case for what some called dynamical climatology rather than meteorology, and what Flohn referred to simply as, quote, the conquest of the third dimension. So with this conquest, the investigation of climate could finally push beyond what had been understood to be mere empiricism, to become a theoretically ambitious discipline in its own right, one which concerned itself less with the useful cataloging or classification of different climatic zones, and more with, as we heard in the introduction, with describing the general circulation of the atmosphere. At the same time that climatologists were beginning to embrace elements of dynamism, as we've seen in the work of Flohn and Petersen, meteorologists, on the other hand, were using physics to push the study of the weather closer and closer to the study of climate. Just as the need for better upper air observations had driven meteorological research during the war, namely to supply the growing numbers of pilots with the information they needed to fly successful sorties, the potential for weather and climate control to potentially be tools of war, to be used in a new Cold War in the post-war period, encouraged US government funding of an ambitious new project to finally deliver on the dream of dynamical meteorology using electronic computers. So here I'm referring to something, again, we might be hearing more about after lunch from Matt, the very origins of the idea of using electronic computers to generate climate models. And in 1950, using simplified versions of Bjerknes's primitive equations, a team led by mathematical whiz John von Neumann and meteorologist Jules Charney, von Neumann is second from the left, Charney's all the way on the right, carried out the first numerical weather prediction using a computer to work out the step-by-step calculations that were necessary to render Bjerknes's insoluble equations into practically useful tools for calculating the future state of the atmosphere. And also, as we already heard, just 5 years after this demonstration, Norman Phillips used the electronic computer to run the weather model for a longer forecast period. And in doing so, he was able to generate a reasonably accurate simulation of the global circulation. This was the first so-called general circulation model. And in this in this way, Phillips's model demonstrated that a computer could be a tool not only for simulating weather, but for simulating climate, which led British meteorologist Eric Eadie to remark after seeing the model for the first time in 1956, quote, "Numerical integration of this kind gives us the opportunity to study large-scale meteorology as an experimental science." So from the start, computer models then were understood to be experimental tools, a kind of numerical laboratory in which meteorological and climatological phenomena could be investigated, providing, therefore, an experimental as well as a theoretical basis for a science that had long been seen as hopelessly empirical. So these models furthered the temporal turn which Bjerknes's dynamical meteorology had begun, integrating dynamics over time to produce long-term projections of climate on a decadal scale. And in so doing, they shifted the study of climate even further into the realm of the temporal. This is the success of these models at capturing regular features of the general circulation, much remarked upon at the time, and notably von Neumann's success in making the case to policymakers and politicians for their relevance to matters of national security laid the basis for their growing and continued importance. By relevance to national security, I mean, von Neumann he advocated for more funding for numerical weather prediction and eventually climate modeling, because he thought that weather control and eventually climate control would become necessary tools to ensure geopolitical security for the West. That we would want to be able to potentially alter weather and climate to defend ourselves against the Soviets, or to increase the wheat harvests in the United States using rain seeding, for example. So computer models would come to play an increasingly and seemingly inexorably central role in the new climate science, which was both resolutely global and concerned with describing climatic change in the doubled sense of both its natural dynamics and, by the 1970s, the increasingly observable and therefore increasingly concerning narrower sense of unnatural or inadvertent climate change. As I said, we're going to hear more about climate models after lunch, so I'm not going to spend more time on them, but I just want to say that this temporal turn in climate science carried with it a corollary which seemed almost incidental or insignificant next to the evident strengths of the new approach. And this was that the physical reductionism that was necessary to create these tools, the reliance on the equations, which replaced the Humboldtian and later the kind of classic climatological attention to the relationship between human beings and climate. So the temporal turn in climate science, aided by computer models, therefore produced a disciplinary separation by shifting the study of climate from geography departments to new institutions built around modeling. And it also produced what we might call an epistemological separation between the physical and the human worlds. Henceforth, different methods would be used to investigating these two areas. And we might say that in addition to this epistemological change, there were also certainly political and I would argue as well ethical and moral repercussions of this sundering of the human from the climate, the study of climate. And here I think the work that Mike Hume has done on the idea of reducing the future to climate is relevant. He's written quite trenchantly on the effect of the increasingly dominant way, this increasingly dominant mode of knowing climate with computer models as a kind of new form of climate reductionism, where all our knowledge about the future becomes located in the sight of these models, which rely upon quite a narrow, as I said, epistemology and set of values. So this is just a kind of marker really to show the evolution of general circulation models over time. So now I just want to slightly trouble this history. Climate models are undoubtedly central to the history of the temporal turn in climate science. But the history of the temporalization of the study of climate has a couple of other key elements that are important to mention. The first is the role of the paleosciences, and the second is the role of historical climatology. So I just want to briefly mention these now. So first, paleosciences. Here too, there's a story to be told of the impact of proliferating data, much of which is derived from using new instruments and new techniques, isotopic techniques, developed in the years immediately following World War II. So we get this explosion of data about tree rings, ice cores, and mud cores. And this was essential in supplanting, as we've already heard, the kind of prevailing vision of climate as being comprised of stable epochs, which changed only on geological timescales, to one in which change could be observed, as we've seen, on a stunning range of temporal scales. And one key conference on the causes of climatic change, held in 1965 at the newly established National Center for Atmospheric Research in Boulder, Colorado, reveals just how self-conscious those who attended were about the nature of the shift in understanding the dynamics of climate, and how much it relied on an interdisciplinary, or at least multidisciplinary, assemblage of scientists. Drawing on both, So this conference was jointly organized by NCAR and the International Union for Quaternary Research, or INQUA, and it was for the express purpose of bringing together those working in paleosciences and those working in computing and mathematics, trying to come up with better modeled representations of climate. In his preface to the edited volume containing the papers from the event, J. Murray Mitchell, a prominent meteorologist at the U.S. Weather Bureau, remarked on the extraordinary shift that had recently occurred in the power of atmospheric science. Quote, he says, "It has only been in the last few years that the atmospheric scientist, in pondering the events of the past, has graduated from a helpless feeling of wonderment over these events to an altogether different feeling of soon being able to construct physical models of atmospheric behavior to help account for these events. The models would," he noted, "soon make it possible for atmospheric scientists not only to describe, but to provide causal explanations for climatic change at the very moment that new data was revealing the planetary environment to possess what he called, quote, an astonishing capacity for subtle mutation and instability." So you've got the paleo data that's producing all of this incredible, finely detailed record of dynamic instability on seemingly all timescales. And then you have ambitions, kind of newly raised ambitions of atmospheric scientists to make sense of it. In 1965, the climatic change under review was exclusively natural. There was no discussion at the meeting about human-caused climate change, nor was there any attempt to project future change. The perspective was distinctly towards the past. But there was, as Mitchell put it, much, quote, debate and confusion over the causes of climatic change, which could, for the first time, be potentially addressed with a combination of novel computer models and what he called a diverse set of evidence for paleoclimates, which were being pieced together in ever richer and more quantified detail by colleagues in a range of allied disciplines: geology, oceanography, archaeology, various branches of the biological science, geomagnetism, and radiochemistry. So this was a very self-consciously interdisciplinary meeting. And despite this newly visible and challenging instability in the Earth's environment revealed by these paleo sources, Mitchell was confident that the interdisciplinary alliance would bear fruit. And in fact, he thought it was no longer an inadequacy of theory that would hold climate science back, but the challenge of establishing the history of the paleo environment itself. Would the paleo scientists be able to keep up with the theories of the atmospheric scientists, was what he wondered. So here we see that the history of the Earth had become a resource, and quite a limited resource, which was needed for the continued production of theories of climatic change. And I think this conference is important because it's one of the first times that we see this engagement between this growing community of paleoscientists and theoretical atmospheric physicists working together to try to understand the nature of natural climatic changes, bringing mathematical problems of climate And this was a conference where Ed Lorenz presented another fantastic paper on the degree to which the climate system can be considered deterministic, concluding that we probably can never know. So mathematical problems of climate in direct contact with histories of climatic change that were revealed by the paleosciences. And they were aware from the start of the distance between the disciplines they hoped to bring together. So this is just a slide to show you the ambitious nature of NCAR at this moment, which had been designed by the famous architect I.M. Pei, who we see there at the right, with Walter Orr Roberts, the NCAR director. It was quite a heady time for atmospheric science. Oh, and I just couldn't resist putting in, these are images from Ed Lorenz's paper on suggesting that the climate may be an almost intransitive system, meaning that it may not be practically predictable, even if theoretically so. It may or may not be deterministic. He says, well, we shall probably never be sure. And here he mentions the relationship between theory and models. And he also referred to these dishpan experiments, which he used data from showing that you could sort of knock a system in and out of different stable states. So this idea of the experimental science was really foremost in the mind, and the dishpan experiments, I think were seen as a key resource at that time to complement the kind of more hard to feel nature of the experimental climate models, but it shows the power of the notion of experiment and the data that it generated. Now, I think I know I'm probably running a bit close to time, so I might just quickly mention Hubert Lamb, because I'm quite aware that many of the people in this room know more about Climatic Research Unit than I do by a long shot. But I think it's important to just mention that with Hubert Lamb, we have a continuation of the kind of a geographical attention to climatology and to historical climatology, which is a really important strand in the late 20th century history of this discipline. It doesn't disappear. It does, in a way, become marginalized, but in other ways, it becomes absolutely central to the practice of climate science, as the unit that Lamb founds is essential in producing global temperature averages that become fundamental to the practice of climate science more broadly. But this is just to say that how do I summarize this? Well, one thing that's interesting here, talking about experiment, is that Lamb really saw data from the past in the same way that climate modelers saw their models. So in both cases, they provided an experimental site for investigation. So he spent a lot of time and energy collating all manner of documentary sources from the past, botanical, archival, etc. And he said, without a record of climate's past behavior extending back over several repeats of the long-term processes of climatic variation, the subject would be like a branch of physics without basic laboratory observations. So if models could serve as experimental sites for climate science, so too could data of past climates. I just wanted briefly to make a point about the relationship between models and policy by drawing on this 1977 report by William Kellogg on the effects of human activities on global climate. So, as I've said already, this temporal turn in climate science, I would argue, entailed the excision of human values from what had previously been a resolutely human-focused endeavor. Now, there's another history of countervailing attempts to understand and even calculate the likely impacts of human activity on the planet, which starts with the 1972 Limits to Growth report of the Club of Rome. And there's also a history of critics or skeptics of the power of models of any kind. And the skepticism focused often on the capacity of these tools to calculate the future accurately enough. But But even some proponents of models identified a more profound risk associated with the tools, and one which focused on the messy realm of politics that lay outside of the domain of models themselves. And here we come to Kellogg, who realized that it was the very sophistication of the models, their temporal ability to predict future climates that actually posed potentially intractable problem for policymakers. And here, I think he identified a kind of key paradox at the heart of climate science. While models provided the means to transform climate science into an experimental science, their very novelty meant that it was unlikely that policymakers could act on it, right? Even if scientists could agree on the prediction of future climate, he says on the right, there remains the question of how useful this information would be. Who would take advantage of it in their planning? We have no experience with how to act, given several decades of lead time. Boy, has that sentence aged well. We've seen in the news lately a lot of predictions that have aged very badly over 2 weeks. But here, I think Kellogg was pointing to something really profound about models, which lies entirely outside the domain of the climate modelers, but in the domain of the policymakers who are expected to use them. Okay, so I'm not going to go through all of this, but I've tried to set out a kind of dominant narrative of the transformation of climate from a science of space to time, briefly. And then I've tried to trouble that narrative a little bit with countervailing complexities, with briefly Hubert Lamb's historical climatology, which was grounded in geographical and therefore very human-centered concerns, and with the tension or distinction between climate models as experimental laboratories and paleo data as a kind of experimental laboratory. Given more time, I'd have explored further the work of calibration and synchronization that is required to make the multidisciplinary science of climate work, which was wonderful to hear Liz mentioned directly today. Calibration is a key tool of climate science. And I think it's one that historians should pay more attention to. And it would be great if the public understood more as well. So a key element of this history is the transformation of climate into a science of change that entailed the exclusion of human affairs from its purview. But that was actually quite an anomalous period in time, I'd say, stretching maybe from the immediate post-war period to say 1980, 81, when you start to see integrated assessment models and other methods that are trying to reinsert the human back into the kind of formal study of climate science, with varying degrees of success. And here I'm going to skip this stuff, but I just wanted to end with a brief discussion of the idea of the Anthropocene, because I know that Liz has done some work drilling one of the cores which the Anthropocene Working Group is going to use. And this concept of the Anthropocene is one of the many ways I think that climate scientists have sought to reinsert the human into their work. And it's a very productively ambiguous notion, the Anthropocene. But at its heart, I think it is also a tool for temporal calibration, offering a way to link human and geological timescales in a kind of systematic and rigorously scientific way, at least in this, as stratigraphers use it. So scientists from around the planet, including Liz, are currently seeking the so-called golden spikes, which might be ratified by stratigraphical methods to provide a starting date for the current geological period. And I was interested to see that this project is being funded in part by the Berlin-based arts organization Haus der Kulturen der Welt, and in association with the Max Planck Institute for the History of Science. So here's a site truly where we see finally historians of science and other members of the humanities coming into it. But the question I want to ask is, once such a golden spike or series of golden spikes has been identified, what might the effects of such a calibration or synchronization of human and geological timescales be? And what might we hope would emerge from it? So if I look back as a historian, I see this effort in the context of a much longer history of the kind of fluctuating set of relationships between understandings of the relationship between humans and climate, right? this negotiation between the human and the non-human. And I think that this range of responses, the popularity of the concept of the Anthropocene, reminds us that this is a question that can never be settled because it's so fundamental. What is the relationship between the human and the non-human, between nature and culture, between human hubris and humility? And perhaps that's a banal thing to say, but I think the deployment of this concept of the Anthropocene in relation to these golden spikes brings our attention usefully to something specific about this moment in history, which is the idea that if we can finally provide a definitive alignment between the human and the geological, that we can somehow tame this problem, that with the tools of geoscience, we can somehow get a grip on this troubled and troubling question about the nature of humanity. So calibration of timescales here is doing a lot of work to reconcile humans and the planet at the very moment when we might consider ourselves to be well and truly at odds. And I wonder if we're expecting too much from this. I'm not saying that anyone thinks that finding a golden spike is going to solve the problems that we face, but that we should seek to do so is an interesting thing to pay attention to. So finally, I just wanted to say that for all the talk of the temporal, the study of climate is always returning to the Earth itself and to place. And these are some of the locations where scientists are seeking golden spikes. So I think it's good to remember that the end of our searching for methods and understanding of managing and understanding time always lies the Earth, and that whatever distinctions we seek to make between time and space are always, in a sense, temporary. They always collapse. Our investigations of the planet bring our attention back to the geographical and the spatial, even as we seek to make sense of the temporal. And finally, as this last slide reminds us, human beings, in all of our many forms and disciplinary identities, are always mediating. We're always involved. And for all the complexity of our current self-understanding of how we do and do not calibrate timescales or fit into nature, it's clear to me that curiosity is innate in us, is natural in us, and to that extent is as natural as an expression of our existence on this planet as anything we could hope for. And I'd just like to end by saying I think that is something to cherish. Thank you.
Hi, Sarah. First of all, thank you very much for a really great summary of basically how historians of science think. You're not the only pigeon or cat in the room, so it'd be great to chat to you afterwards. This is very squeaky. I was interested. Sorry. So I was interested in this sort of narrative, that you complicate very rightly. Mm-hmm. But I was wondering, as a historian, sort of complicate this narrative a bit.
I'll repeat your question. How's that? I can repeat the question for the folks at home.
So you talked about Hubert Lamb. You talked about this 1965 conference.
Mm-hmm.
Reed Bryson was one of the names that
Mm-hmm.
I noticed on there. 1965 is a very interesting time because this is just before the 70s, when we have these huge cultural and economic changes that completely transform not only general society but also academic society as well. Environmentalism sort of coming to the fore, etc. So 1965 is an interesting time to look at. So I'm not sure if there's a continuation. I think there's a change, especially in Reed Bryson's story. Like Reed Bryson was complaining about the human being taken out of all the stuff that ecologists and climatologists were doing right up until 1980. And I think Hubert Lamb as well, in the early 70s, he obviously left the Met Office, and there's this conflict there about having this funding cut, all this sort of spatial sort of work that you're talking about. This is in the 70s. Mm-hmm. So I'm wondering what you think about this idea of a transition transition being complicated by the events of the 70s and the changes that were happening during that decade.
So just, I can't summarize that all, but basically, how do we distinguish in our accounts between the concerns and the context of the 1960s and what later happened in the 1970s, especially given the rise of more widespread environmental concern? I think, is that fair to put it? I mean, I guess I agree with you. There is an important shift that takes place there. And I hope I didn't suggest that. I mean, one of the things in this talk I didn't do was really talk very much about the discovery of global warming or any of that, because I think it's important to note that the study of climatic change, interest in it, comes before and is really necessary for, I mean, it's in an internalist sense, it's necessary to have the data on natural variation to be able to detect human variation, right? But it also happens to be the case that it wasn't until the early 70s that there is a kind of enough broader concern where it does not, that climate doesn't become an environmental concern until then, really. It's a kind of niche topic, I guess. So, and I think that, why does that matter? Because the disciplinary frameworks that people are working in persist more or less across those, they don't change as quickly as we get the kind of changes in culture, actually. I mean, you've pointed to one important change, which is this moment where Lamb leaves the Met Office and founds Crew, and we get a sort of new island, a new institutional island emerging, and that is important. But I guess my perspective on this I seem to always be drawn back to the role of disciplinary training and perspective in shaping the way people do science, and how important and painful it is to acquire those things, and then how very difficult it makes it to actually be interdisciplinary. And when we talk about interdisciplinarity in climate science, there's often that's just pure rhetoric. Really it's all about the physicists or the computer models, and they talk a good game, but they don't really mean it at all. So that's at the level of discourse. Then you have the level of how people actually work together. And then there's a whole, I guess, more recent history that I'm not familiar with, where you have people who really truly do have training in what we might think of still as somewhat separate but joint disciplines. So that's a slightly meandering way of answering the question, which is to say that, I guess, there's continuities and discontinuities in how we think about it. But I agree with you. That's one of the reasons I'm personally fascinated with this period before the discovery or concern about anthropogenic climate change, because we can see more clearly, in a sense, the disciplinary framings of understandings of climatic change, which are the ground upon which the discovery then of anthropogenic change must grow. So in a way, it troubles Joanna's history, because the history that she told is quite, in many ways, quite distinct from the history that I've told about the transformation of climate science from a geographical to a physical science. So I think there's more work to do to bring those together, and it's important not to get ahead of ourselves, as it were. And that's why it is good for me. I find it very interesting to go back to these moments in the 60s where the concerns, you almost want to shake them and say, but don't you see? But that's the point of doing the history in the way that enables the then present to speak in its own terms.
One more question, Peter.
So can I just pick up on your last points and maybe make a point that I think is potentially relevant to this in terms of the reframing of how the science is being done, so that in the latest, if you look at the latest IPCC report, 6th report, you'll see how the framing of that has moved away from temporal in terms of trajectories of global warming over time to much more spatial. If you're talking about where it's framed in terms of what are the temperature, rainfall changes, etc., for particular degrees of warming. I think we may hear from Richard Betts and others this afternoon about this sort of aspect of it. So I think this is relevant to the critique, it seems to me. So,
thanks, that's great. Yeah, and that's why I use this phrase a kind of historical anomaly in a sense, because I think we as historians of science have also been guilty of kind of tending to see the rise of the kind of climate model driven temporal focus as being continuous and continuing. And in fact, I think there's another way of telling that story, which is partly to say the geographical never went away. And there was a lot of work that was done to integrate these things, and the whole history of paleoscience in some way points to that, but also that there's a more recent and complicated history of attempts to step back from a purely temporal logic, and also that logic of excluding the human. So yeah, I'm interested to hear you say that. I thought you were going to talk about regionalization and more of a focus on regional climate change.
I think just very briefly, I think people get fascinated to, and maybe this is already happening, to look at the latest way in which the IPCC is working across the working groups. Because that has evolved over time. And to look at the latest assessment and critique it in the sorts of ways that
trying to. Yeah, okay, thank you. Okay, lunch, thank you all.
Thank you very much, Sarah, for the talk that's linked human history to climate change. And that's the core of this meeting, bringing the two together. Thank you very much.
Thank you.
The first speaker of the afternoon will be Professor Tim Osborne, who is now head of the Climatic Research Unit at the University of East Anglia, and he's going to talk about how we study recent and current observed climate, history of the development of key instrumental data sets. Tim.
Chris, hope you had a good lunch, everybody. I would say that I'm not going to go through this in a detailed chronological order. I'm instead going to pick out a few issues or concepts or approaches that people have taken. And I'll say a little bit about when they were introduced. And I'll just add something right at the very beginning that I hadn't intended to say, but because we've heard Hubert Lamb mentioned a couple of times and the Climatic Research Unit, I'd say that even within the lifetime of the Climatic Research Unit, which is 50 years this year, there have been quite dramatic changes in the approaches people have taken to this. So Hubert Lamb was the first director, and he had a project to map out the climate of the last 2,000 years, I think. And his approach was very much going to be, get a big sheet of paper, draw on it, mark little pointers and numbers where you have some evidence for some particular source, and then get an expert to draw climatic maps. And Tom Wigley, I think, who was the second director, but at the time he was employed to work on this project, said essentially, no, that's not the way to do it. What happens if you get more data later on that disagrees? You're going to go back and redraw these maps? You need to do something that's more objective, more quantitative, can be reproduced when we have updated information. And as I understand it, they kind of fell out a little bit at that point. So there's difference in approaches. And of course, the other thing that was mentioned was this, perhaps this tension between observational and model approaches. And I think Hubert felt that, especially perhaps in terms of competition for funding and things like that. And it's nice to reflect back now when we think that some of our best insights into historical climate change come from bringing together models and observations in the form of reanalyses. Nearly everybody uses those for many things to understand past climate change, and that clearly shows how bringing together those two things enhances our understanding. The first concept I'm going to just talk about is, if this will work, how do I do this? Yes, is this nice graphic from Ed Hawkins to talk about why we're actually interested in the global temperature, why the global scale when, what affects us is the local variability of our weather and climate. And here we see the central England temperature record with different degrees of temporal smoothing in red, and occasionally you'll see the global temperature record in black. And you'll see that this highlights that what we experience is a mixture of unforced variability, especially due to natural variability of the atmospheric circulation, superimposed upon the response to external forcings like greenhouse gases, as we heard this morning. And so if you're interested in, perhaps as Hubert Lamb was, in the kind of local scale and perhaps on either on short timescales or on timescales where the external forcing is quite weak, then you get focus in on the atmospheric circulation variability and less on the forced changes in climate. But if you're in a period where the climate forcing is becoming quite large on the longer timescale, as you can see here, then you can't do without the forced signal, even if you're looking at the local scale in the central England temperature. But in order to identify and detect and understand the forced response, you need to go to the large scales. So you need global patterns or global averages. And this was understood, I think, already by Callender, was mentioned earlier on. He was trying to identify in his 1938 paper a warming signal from CO2 that he expected or calculated would be less than 0.1 degrees Celsius per decade. So he was looking for something really small, and there's no way he could find that in a noisy local record. So he understood why you had to go to a global scale if you could. I'll skip that slide because I said everything that was on it already. So if you want to go to a global scale, then you need networks of data. You need to compile it. Ideally, they need to be standardized in some way so you can compare them with each other and over time. I've got some non-exhaustive milestones in the next few slides. Just picked out a few things that sprang out to me. So on the land observations, then there was the initiative from Mannheim in 1781 onwards. That was trying to get a network of observations of land temperatures with some kind of standards of how to observe them. Obviously, we know about Stevenson screens, which tended to be introduced in the late 19th century and beyond. The predecessor to the World Meteorological Organization in 1873 was trying to expand these initiatives, and it led to data sharing by the end of that century. And particular compilations that were widely used and still are widely used to the weather records and the monthly climatic data for the world. And they came in the kind of partway through the 20th century there. Marine observations I know less about. I put a few things in here. I think a crucial milestone was related to Maori and the various initiatives there in order to kind of standardize how observations at sea were taken. These were compiled digitally in the mid-60s, and that led on subsequently to things like the Comprehensive Ocean Atmosphere Data Set, which is now the international COEDS. So there's a few milestones there in terms of the background to the materials you need. And then in terms of what people have done with those materials, I picked out again a non-exhaustive list. We've already heard about Copen and Callender a little bit. Interested to me that they were already, even back then, understanding and trying to deal with some of the issues that we still grapple with today, issues with data quality and homogeneity, how to cope with observations that are unevenly spread over the planet. I've mentioned Bodico here because that was quite different in that they took hand-drawn maps approach and perhaps less objective, but it could bring in ocean data because all the other ones were land only. And then we get through to the 1980s where you've got the organizations that still produce global temperature data sets through to this day. NASA GIS with Hansen, Jones, Wigley and colleagues at the Climatic Research Unit where I'm from, producing these gridded data sets of temperature anomalies. And although homogenization had been considered before, for example, by comparing a station against its neighbors to see if you can see some spurious jumps, in the mid-80s, CRU undertook the first attempt to apply that to a global scale network and not just to discard series that have been identified as inhomogeneous, but to actually try and correct them where you could. And then the kind of first true global series that's regularly updated that combines land and oceans was put together by Crew in the 1980s, but taking the sea surface temperatures that Folland and Parker and others at the Met Office have been working on. So although that particular study was not a link up between CRU and the Met Office, pretty much all of the updates and further improvements since then have been. So had Crew T, had for Hadley Centre at the Met Office and Crew for Climatic Research Unit. Fortunately, I didn't have to try and pin together, as Joe did with cut and paste of Callender's record against the modern ones, although she showed it very nicely. And Hawkins and Jones actually did this to see how similar Calendar's record was to the modern data. And as you said, Joe, they're surprisingly good considering the materials that Calendar was working with at the time. So these early records do show similar results to the later ones, not always the case. Here I'd say on the y-axis, we've got temperature change or a temperature anomaly or departure from some reference level. So the concept of anomalies is a really important one in making these global temperature data sets. And so I've got a couple of animations to try and illustrate why we might want to use temperature anomalies rather than absolute values. So here is a video of a few years of temperature station data. These are absolute values with different colors for warm and cold, as you can see. And there's lots going on here. You've got a seasonal cycle, you've got geographical variations, distance from the coast or mountainous areas being colder, as well as interannual variability, which is perhaps what we're most interested to understand. And so one thing you can do, therefore, is to, there goes the animation. One thing you do, therefore, is to think about a climatology for some kind of base period. So often we use 1961 to 1990, but others periods have been used. And that's in the color behind this. And this is a kind of a fixed time invariant field. It varies with the annual cycle, but not with any other aspect of time. And what we can do is to use that to separate out our information into a kind of a time invariant part, and then the anomalies as the subtraction between the observed station data and their means. And we get the anomalies like this, which is again another animation, but now of the temperature anomalies. Color scale is the same, so these are much smaller because we've got rid of lots of this variability. And in fact, if we expand the temperature scale and have the animation with a more refined temperature scale of just plus or minus 5 degrees Celsius anomalies, then you can start to see these coherent patterns of change. So that's the kind of background to what the anomalies are. And so this separation into a kind of time invariant fields that capture the geographical patterns at the annual cycle, but nothing else. And then separately, the time varying anomalies. That's got many benefits. We've already seen on those animations. It simplifies some of the spatial structures, so you can do better at spatial interpolation. It also reduces the impact of changes in data coverage, perhaps if your observation network changes over time. It also reduces the impact of differences in measurement practice, differences in how thermometers are exposed, differences in microclimates. So these latter aspects can give materially different mean levels, but they give much less effect on what the changes are over time, unless, of course, those aspects themselves change over time. For example, you change your thermometer exposure. Those introduce inhomogeneities that we still have to deal with. I think is my next slide. Nope, slide after that. So when were the benefits of using anomalies first realized? I'm not sure, because people seem to just use them as if it's obvious that you should use them, and they don't necessarily say this is why we're using them. So Calendar in 1938 used anomalies. They didn't say this is why you should use them and cite some earlier study that had demonstrated it. And even Dove in the 1850s was looking at anomalies to try and reduce the effect of elevation when he was plotting isotherms across the world. Disadvantages, though, especially, is that you need to have an estimate of the climatology for your reference period for your particular setup, your station, its location, instrument, etc. So a more recent development, still part of the history, of course, is that Berkeley Earth introduced a similar approach, similar in that they separated out into deviations from expected values, but their expected values were no longer a fixed reference period. So they could now use short segments of data, even if they didn't have data for the 1961 to 1990 period. And that opens up many possibilities, including how you might deal with the inhomogeneities that I mentioned, because you could just split your records up into shorter segments, and their method allows you to it's a short segment, even if it doesn't have data during the reference period. So just a slight diversion into inhomogeneities. This is one example, is the exposure bias that happened when there was a change from older types of exposures to the Stevenson screens. And these next two slides come from my PhD student, Emily Wallace. She's also got an animation here of for the countries where she's managed to get adequate data so far, she's made an animation of the types of exposure in place. So you'll see over time, the year is at the top there, you'll see over time a gradual transition in most places towards red dots, which are the Stevenson's type screens, from, for example, North Wall exposures in green, or in orange you've got some open exposures like Montsouris screens and glacier stands. So there are some changes and they vary over time, and we need to take this into account when we're using some of the early data. And the reason why we have to take them into account is because the thermometers in some of the early exposures would read a different value than in a Stevenson screen, even without the climate changing. So the second slide from Emily gives an example of that, comparing what we call open screens against Stevenson screens. And we can see annual cycles of exposure bias in the maximum temperature, the minimum temperature, the mean temperature, the third plot there, and the diurnal temperature range on the right. So we see that the Stevenson screens tend to read cooler than the previous open screens, especially in the summertime, and the differences are biggest, but they're still present. So biggest in the maximum temperature, but they're still present even in the mean temperature. So that's an example. And many authors have understood the need to consider those very carefully over many years. And in fact, even the introduction of these standardized methods was partly because it was understood already in the 19th century that you need to be very careful in how you're measuring these the temperatures. If you want to get a consistent record, you need to have some kind of standardization. The next topic I want to just briefly cover is how many observations do you need to estimate a global temperature? Various different authors in the 80s and 90s tried different approaches to how you might estimate that. The result depends upon the timescale. If you want individual seasonal values, you might need 40 stations, annual timescales, 20 stations, 10 for a decadal average, but only if they're well distributed and perfect. In practice, they're not, and therefore we need many more than this, because then we can use the overlapping information from nearby stations to try and address some of the imperfections in the data. I will just give a quick guide to one thing we did to try and understand this. What we've done here is to take the station data of monthly temperatures and correlate each station with every other station in the network and plot that correlation against their separation distance. And you get this huge cloud of grey points, but actually 50% of those points lie between the two thin lines there, and the thick line is the median of the data. And you might therefore say, well, we can know something about the climate if we have an observation that's correlated with our location. So maybe correlation of, arbitrarily we might say correlation of 0.5 perhaps is what we would consider enough. So typically you can go out to more than 1,000 kilometers away and the monthly temperatures will be correlated at that level. So at the bottom here, we've got maps of the spatial coverage of stations in 1875 on the left, 1900 in the middle, 2010 on the right for the land data only. And we could therefore draw circles of radius 1,246 kilometers around each of those stations to get an idea of what kind of region those stations are telling us about. And therefore we would consider we've got the land surface covered pretty well in the modern period, but perhaps in 1875 there are big parts of the tropics that we're not knowing much about. But if you repeat the analysis using annual means rather than monthly, you find that the correlation distances grow up to 1,476 kilometers, and therefore the size of these regions of information grow as well. And if you go to decadal, it's harder to calculate these things because the correlation doesn't decay quite so clearly with distance, but you could still arbitrarily choose something where the half of the stations have a correlation of 0.5 or above, and therefore say that on the decadal timescale, our stations are telling us about areas indicated by those circles. So we have much better knowledge of decadal timescale variability in the 19th century than we would do about individual months. I've not said much about the oceans. Chris will probably be hoping I'll say a bit more than I am actually going to do. I would say a particular concept here is that sea surface temperature has mostly been used over marine air temperatures. SST varies more slowly, has a smaller diurnal cycle, so you can estimate monthly means with fewer observations. Also, often half of the marine air temperatures are traditionally been excluded because they were measured in the daytime, and they're often biased by the heating of the ship superstructures. I think in recent years, nighttime marine air temperatures have been increasingly used because although they have biases, they're different biases than we get in the sea surface temperatures. So there's value to utilising both types of data, and I'd like to say more about that, but time doesn't allow me to. Instead, I'll just give a shout out to our current GLOSAT project, which is led by Liz Kent at the National Oceanography Centre. And this graph comes from them, from Tom Cropper in particular. We're trying to go back before 1850. And if you want to do that, you can't use sea surface temperature, because in the top graph here, maybe a little bit tricky to see, but the flat lining before 1850, or not quite flat lining, but the number of observations of SST is very low. And yet we do have still a reasonable amount of marine air temperature coverage in certain parts of the oceans. The other issue is they've got to grapple with this daytime issue, because before 1850, the percentage of those observations of marine air temperature taken during the day grow very high, towards 100% early on. So I'm going to finish with a few slides if I've got time to say what have we learned from the global temperature data sets and a very recent change. So how much has the world warmed, which is relevant for policy goals such as Paris? We might take the decade at the end of the record, compare it to the 19th century and get an estimate of 1.1 degrees Celsius. We take into account, of course, that the climate is warming about 0.2 degrees per decade. So already at the end of that last decade, we're actually more like 1.2 degrees Celsius, with uncertainty coming, especially from this early period, about plus or minus a tenth of a degree. I meant to remove that because of lack of time. This is looking at zonal averages. So you've got temperature change over time on the x-axis, from the South Pole to North Pole on the y-axis there. And if we, for example, take the period from 1960 to the present and say, how do the temperature trends look as a function of latitude, then you see a very clear polar amplification in the northern latitudes and Arctic amplification. If you do the same thing for land and ocean separately, you find the land-ocean contrast in the amount of warming. And actually, you can also see a reduction in the amount of warming in the subpolar oceans. The point thing here, and this probably links on to Peter's talk later, I hope, is that we understand the mechanisms that cause these patterns, and we can see them in the observations. And I should stop there, Chris? Yep. Okay, can I go to my conclusions then? Just recap on some key points. So even though we have a robust record, there's more to this than just routine updating. There's still research to be done, pushing back to earlier periods, as I mentioned. The thing I skipped over at the end there was some recent reductions in biases and homogeneities. It's rare that those dramatically alter the global scale picture, though, although the most recent update did. In terms of HAD crew T5 compared to HAD crew T4, the warming since pre-industrial was about 18% greater than we previously estimated. And then the milestones, I won't recap them in detail other than to say the key things that allow this to happen are standardized measurements, sharing and building of compilations of the data. And then what we then do with others around the world is to try and use those to get the best estimate of global temperature we can. Thank you.
Time for one question. Any questions? Okay, then we'll carry on, I think, to the next talk. So the next talk will be by Professor Matt Collins from the University of Exeter. He's Joint Met Office Chair in Climate. And how do we model climate? History of the development of past and present approaches, and how might future modelling develop? Matt.
Thank you very much, Chris. In putting this talk together, it turned into more of a personal history of climate modelling. And so I'm going to draw on a lot of my own experiences of this over the past few years. How do I click forward? Shows how good I am at operating technology. Okay, yeah, I did have a background. Okay, so this is a list of some events in climate change science and climate modelling in the last 100 years. It turns out that the 2-year delay in this meeting means that climate modelling is now 100 years old. So we'll all sing happy birthday. So starting with Richardson's dramatic failure of trying to do a weather forecast with pencil and paper, through some of the things we've heard about already, Callender, von Neumann, Charney. I thought I'd mention the Met Office, Bushby and Hines, doing their first experimental weather forecast. And I understand actually when Sir John Mason became Director General of the Met Office, in those days, the forecast was really just done by hand. And he said, no, we're going to take these guys and take their experimental forecast and actually use that. So that was a great leap forward, I think, in the UK. NCAR, we've already heard about. Manabe and Weatherald, first mention of long overdue Nobel Prize, I think, in climate science. You can try and spot the other co-recipient of that Nobel Prize later on. And then going into the sort of more modern era, Met Office models, IPCC, Charney report, etc., etc. So I thought I'd just pick out 2 of these things. I mean, there are many people who have told the story of Richardson's dramatic failure, by his own admission, a dramatic failure. And I think, they've told the story better than I can tell it. So Peter Lynch has a very nice book about this and a very nice article in Weather where he talks about the Richardson Forecast Factory and this interesting painting of how that was going to work. And also, if you go onto Peter's website, you can get the Fortran code to repeat the Richardson calculation and also repeat it in a balanced way. So the reason it was a dramatic failure is because he didn't do a data assimilation, what we now call a data assimilation phase, to get the observed on the trajectory of the model or the trajectory of the equations. So that's a nice, right at the beginning of modeling, and I just picked up again, sort of almost at random, this study by Hansen in 1988, where he does a series of predictions, with a very coarse resolution climate model, or projections nonetheless. So the vertical dash line there is the point at which his study was published, and the coloured lines are the various different reconstructions of the observations. This is global mean temperature, as Tim just talked about. And Hansen has 3 scenarios, an exponential growth in CO2, probably about spot on, a slowdown in emissions, and a rather optimistic 0 emissions after the year 2000 scenario. And I think you can see, at a very basic level, that climate modelling works, right? Because the observations lie within the range of scenarios produced by the model. So 1988, a few years later, was about the time I got into the game of climate modelling. Started my PhD in 1990. Here you see in the picture my cohort of fellow PhD students. Not sure what happened to these guys. Hopefully they've done something useful with their lives. My PhD was on the atmosphere of Mars, the circulation of the atmosphere of Mars, using the Reading spectral model developed by Hoskins and Simmons. And the first thing that happened on day one is that Ian James, my PhD supervisor, said, I've made some changes to the Reading spectral model to make it suitable for the atmosphere of Mars. It doesn't work anymore. Can you fix it? And with that, he handed me a thick wodge of 80-column dot matrix printer output. And I thought, well, I've done programming. I, grew up doing programming basic in my bedroom as a teenager. I'd done a bit of coding at undergraduate level, so I thought I can fix this. So I took this big wad of paper back to my desk and opened it up and found pieces of code which looked like this. So this is Fortran. It contains, I think, some fairly difficult to understand, let's say, coding. So it's organized in deck form. That's a kind of throwback, I think, to the days of punch cards. It has these common blocks. So I was used to, when you wrote a subroutine, you passed in the variables that you needed. But this had common blocks. It also had something, equivalency of arrays, which I'd never come across before. But so there's a line in here which equivalences a 4-dimensional array to a 3-dimensional array. The reason for using these common blocks and this equivalencing are all to do with basically efficient management of memory, because memory was at a premium then. And these are big models, because obviously you've got grid boxes in the horizontal and vertical. The code had these kind of line numbers, so you had to use a program called update, so you couldn't just go in and hack the code. You had to find the line where you wanted to insert your code and insert after that. That usually caused a lot of errors. So often you'd be waiting for several hours for your job to get out of the queue into processing, and it would fail immediately because of a syntax error. Or in one case, when I left my program running over the weekend, I had got it into an infinite loop, and I burnt up all the PhD student allocation of computer resources on the Imperial College supercomputer. Luckily, we had only been given a very small fraction of the Imperial College or the total UGAMP allocation. And yeah, as I say, the experiments were performed on this Imperial College HPC, I can't quite remember what computer that was. Don't know if anyone else can remember, but at the time, ECNWF had a Cray YMP with 512 megabytes of memory. To put that into context, this iPhone has 64 gigabytes of memory. So this is 100 times more memory than we had at that time. It also had some comments, which were thankfully quite useful, although I did once get a piece of code from Paul Valdez to do the stationary wave calculation, and it had one comment in the first line of the code that said, do not change anything below this line because it won't work anymore. So needless to say, that wasn't the most successful calculation of my PhD. After my PhD, I went actually to Oxford to do a postdoc, and we turned that Mars model into a kind of more realistic Mars model. And we actually used that with the European Space Agency in mission planning, believe it or not. But after that postdoc, I went to the Hadley Centre, and sort of the late 90s, turn of the millennium, and I think this was actually really a kind of golden age of climate science and climate modelling. So the models at the time were HADCM2 and HADCM3. And, because they were atmosphere models coupled to oceans, and because they had increased physical processes, for example, aerosols, it meant it unlocked a huge number of scientific questions that we could look at. Detection and attribution, which I'm sure Peter will talk about. So now you could simulate the historical period. Climate sensitivity and feedbacks, associated with clouds, water vapor, sea ice, that kind of thing. All those processes were represented. Future scenario projections, which were the funders were very keen on. I personally was working on El Nino, and also, later came the ability to simulate the carbon cycle, and Peter Cox's famous paper over the Amazon dieback. I thought I'd show another piece of code at this point from the Met Office climate model. Again, it's quite tricky to follow, and if you've ever used the Met Office model, what happens is all prognostic and diagnostic variables are stored in one array called the D1 array, and this is so you can again do dynamic allocation of memory, so you can maximize your use of the relatively small memory footprint of the supercomputer at the time. So in order to access some variable within the D1, you needed to know where it was. So there are pointers in the code which allow you to point, in this case, to the temperature. And there are arrays of pointers as well. So it just all got incredibly complicated. And I never once attempted to modify the code in any way because in any part that was important for the running of the model, if you like, because it was so complicated. About that time, climate modeling was getting to be a sort of global phenomena. The Japanese government invested in something called the Earth Simulator. It was the most powerful computer in the world at that time, dedicated solely to weather and climate modeling. This is a picture of the Earth Simulator. So the blue cabinets, they're about, you don't get much sense, they're about 2 meters tall, a bit taller than me, 1 meter by 1 meter. Each cabinet contains 2 NEC SS6 nodes. And again, each one of those nodes had 16 gigabytes of memory. So 32 gigabytes in one of those big blue cabinets and 64 megabytes in here. I was lucky enough to go out to the Earth Simulator or to run a few jobs on the machine. They took me once into the room to see it, and I can tell you the experience is deafening because the air conditioning was so had to be so powerful. And although it looks very sort of sleek and Japanese, if you open up one of the floor tiles, there's a big spaghetti of wires which joins all the different nodes together. So that was quite an experience. For me, the 2000s were really the sort of era of climate ensembles. So this is when we started recognizing that just doing one realization wasn't enough. And two things happening around this time. One was the development of something called the Coupled Model Intercomparison Project, moving on from the Atmospheric Model Intercomparison Project. So this was, running models using the same forcing scenarios, collecting the data and sharing the output. So now you could write papers not just with your model, but with all the models in the world. So that's one of my early papers on using the CMIP1. And the other thing that was happening, Miles Allen suggested that we could run climate models on people's home computers. Again, because HADCM3 has is so efficient in its use of memory, it means that you could actually run a model in single precision on a PC of that time. Probably had about 128 or 256 megabytes of memory. And the experiment that we did with the climateprediction.net was to perturb parameters, sometimes called perturb physics. In that time, I'd been on a sabbatical at the University of Reading, but then I had gone back to the Met Office, and probably the 2000s was the decade in which I spent my most CPU cycles of my career in running these ensembles for eventually for the UK climate projections at 09. And the idea here was that not just to get the best estimate of what the climate change signal is, but to think about the uncertainties as well. So here we see projections of UK rainfall ranging from very dry up to sort of no change. So there's quite a big uncertainty range, particularly at this kind of regional level. To get this picture, I had to go to the UK CP09 website and found that it's in the National Archives. So that says something, I suppose, about, well, at least it's in the National Archives. It was considered to be useful enough to be archived. We were, bashing this Cray T3E. That T3E was moved from Bracknell to Exeter when the Met Office moved to Exeter, put on the back of a lorry and taken down. I think someone knew that this was going to work, but there was an amount of skepticism among the scientists about whether this kind of bump, going down the A303 with a Cray T3 on the back of a lorry was really going to work. Everyone was told to stop I forgot to stop my job on the T3, and when they plugged it in Exeter, it restarted. Amazing. amazing feat. Moving on a bit further in time, we get to IPCC AR5, so Intergovernmental Panel on Climate Change Fifth Assessment Report. Here, I think the multi-model is starting to become king in terms of looking at future projections. So we've got projections of global mean temperature on the top here. The 39 indicates that there are 39 separate different models, some sharing some components. So this kind of activity, involved a lot of flying around the world to exotic locations, principally to argue about how to do the stippling on the graphs at the bottom here. And I think I ought to mention also at this point a posthumous mention for my colleague Gert-Jan van Oldenburg, who did a lot of the data wrangling to get these kind of figures in the shape that we needed to. He sadly died a few months ago. So I'm trying to look at my timer. So what about the future? Well, we've had IPCC AR6 now, and we've had CMIP 6. The CMIP project seemed to skip a few numbers at some point, so there was no CMIP 4, I think. But I think now, we're getting to a point where we're recognizing climate change as, being a sort of global geopolitical issue that really needs fixing. And, you might argue, are we done with climate science? Have we done our job, and we really should be investing in science that for mitigation, renewable energy and that kind of thing. I actually think that we're not done. And I think what we really need now is a kind of renewed focus on regional climate change. And that regional climate change really for adaptation planning, which I'm sure Rich will talk about, designing climate solutions, which are not going to involve just one action. And also, I think we really need to closely monitor mitigation actions to make sure that they're not doing things that we didn't want them to do. A little sort of sobering picture, I think, of where we are with climate modelling, particularly when it comes to regional climate change. So what these figures show are, so they are multi-model averages of rainfall from the climate models minus the observations. So these are the biases in the models. And what you see actually, particularly if you live in the tropics, is that there are some quite large biases in positions of tropical convergence zones, monsoon areas. And if we go from the CMIP 3 models in the mid-2000s to the CMIP 5 models in the early 2010s, up to the present day CMIP 6 models, what we see is actually that we really haven't made as much progress as we should have done in terms of this regional climate change. So, in terms of using these models for future projections, this is a big issue still. The other issue that so that's kind of like an old problem. This is a new problem, and I don't test me on what all these lines mean, but this is basically an indication of the advance of supercomputing performance. And as we see, so it's a log scale on the y-axis. So going from the 70s to about the year 2000, we could rely on this Moore's law of supercomputers increasing, doubling in power every couple of years. But that has now kind of tailed off. So if you look at the blue curve, which is a proxy for the power of a single microprocessor, that's kind of leveling off. The frequency, or the sort of clock speed, that leveled off a while ago. So the only thing you're left with really is being able to fit more and more transistors or more processors into your supercomputer. So we can increase the number of processors, but we can't necessarily increase their power. The other thing on this curve is, of course, that even though the typical power that you need, the electricity that you need to be able to run one of these microprocessors, that's kind of leveled off a bit. But as you get more and more, the power consumption of these supercomputers is really becoming a big issue. So, I think there are a number of things talked about for the future. A lot of talk at the moment about use of machine learning and artificial intelligence techniques. I think that has been demonstrated for things like speeding up parameterization of parts of the model, radiation, for example. Also, actually, some new results suggesting that we can learn about parameterization schemes from higher resolution models or even observations. There are some projects out there even looking to replace the whole of the model with machine learning. And in fact, there's a recent paper that's demonstrated this. It kind of looks realistic, but you worry about things like for climate conservation of important quantities, energy, moisture, etc. And increasingly, it's used for post-processing of output. On the kind of use of new computing architectures, well, I'm sure there's lots of things going on. A couple of things I know about is that there's some work in Exeter looking at algorithms which use parallel in time. Now, don't ask me how it works because it seems almost impossible, but I'm sure it does. And also, in these atmospheric models, representation of convection is probably one of the most critical processes, and that's something that we don't get very right in our low-resolution climate models. I'm coming to the end, Chris. So in summary, I think climate models, of course, have been essential in our journey of climate science because you can do experiments, you can do counterfactuals. I hope I've demonstrated that the modeling and the computing are sort of inextricably linked, and that's going to be the case going into the future, where we're going to have to think about doing new techniques for modeling. I think the current and future science and policy questions move us from the global to the regional scale. So climate model is still relevant, but we still need to solve some age-old problems in that domain. And just to kind of end, perhaps with a rather trite observation, that actually, although we've been immersed in this, many of us in this room, the idea that you can actually write 1 million lines of code or near to 1 million lines of computer code using some ancient programming language, Fortran, and it ends up resembling something as complex as the Earth. I think that's a bit of a triumph, actually, for humankind, or at least a triumph for scientists. So, thank you very much.
Thank you very much, Matt. I think I'll start the question this time. You didn't mention a possible problem, that it may not be a problem, that many leading models now have increased climate sensitivity. Can you comment on that?
Yes, I probably could comment. Well, perhaps for the non-experts in the room, the climate sensitivity is a sort of property of the model that you don't build in. You don't have a routine that says the climate sensitivity is X. It emerges out of all the feedbacks and processes that you put in the model. And I think, those models which do have a climate sensitivity also have improved representations of those physical processes, notably clouds. So there's something of a conundrum here, I think, in the sense of, basically improving the model ends up with a high climate sensitivity and then somehow is perceived to be not good, whereas actually it's been improved since the previous version of the model. So, I think that's an outstanding question that we need to grapple with. Some modelers would probably tend to believe their models more than they would the pesky observations and all their errors.
And any questions on the floor? Yeah.
It's a really interesting talk. I was really fascinated by what
you're gonna get the microphone. You're gonna get feedback again.
Testing.
No, you're too close to the speaker. So perhaps move.
Yeah. Sorry. I was really interested in what you're talking about, the sort of labor process of coding in the 1990s.
To what extent are these codes archived and accessible to historians going back? I don't know if you know, but I'm really interested.
Yeah. So Brian's got some printouts. No, actually, that IGCM code, that Reading spectral model code, did come from Mike Blackburn's website, so that is available. Whether you can find a Fortran compiler that will actually be able to compile it is another matter. But yeah, so there is some archiving of this.
The original thing had one comment which said University of Reading.
Okay. Okay, we better move on to the next talk, which is being given by Peter Stott, who is professor at the Met Office, and he's deputy head of the Hadley Centre. And he's going to talk about the development of ideas about humankind affected past climate and what we expect in future.
Thank you, Chris. I also have a day a week at the University of Exeter with Matt and other colleagues as well. So, oh, hang on, I've got to do something. Hang on. Oh, there we go. Right. So, yes. So that says that, and so actually my talk builds really nicely on the two previous talks from Tim and Matt, because my talk is really about what happens when you bring the observations and the models together to tell you about causes of past climate change and what that implies for the future. So it happens I've written a book, Plotter, The Inside Story of the Battle Against Climate Change, available from all good bookshops, which is also, of course, a bit like Matt was saying about thinking about the history of all of this, has certainly caused me to reflect quite deeply on the history of the subject and my own role within that. And some of the reflections that are going to come will be coming out of that thinking process that went into writing the book. So we've seen from Tim, of course, graphs of this sort. This is a snazzy version of HadCRT, you might call it, that's been produced by our graphics colleagues at the Met Office, showing the rise in global average temperature up and including 2021 as annual averages, with a warming of, temperatures are now about 1.2 degrees Celsius relative to pre-industrial levels, if you take 1850 to 1900 averages as a representative of pre-industrial temperatures. And as we heard from Joe, of course, about the very well established facts of the greenhouse effect, and this remarkable graph, which I'm not sure we've seen yet, of the Keeling curve of CO2 concentration as measured from the summit of Mauna Loa volcano in Hawaii, showing this relentless increase in carbon dioxide concentrations into the atmosphere, then a priori you would expect that this is going to be having some effect on global temperatures. But the question that the scientific community asked itself here was this effect significant? Were we now seeing a significant effect of the enhanced greenhouse effect from emissions of greenhouse gases into the atmosphere from burning of fossil fuels and other causes? So I want to take us back to the mid-1990s on this to rewind the curve back to, I'm just showing you the CO2 concentrations. And again, in a slightly personal reflective note here, to start really with a paper by John Mitchell over there. This was a seminal paper published in 1995 in Nature. And this was just before I applied to go and work at the Met Office Hadley Centre. And actually very much the reason I applied and then really wanted to go and work in John's group over there. And this was, at least to my understanding of this, the very first successful simulation of the past evolution of global temperatures made by the HADCM2 model we've just heard from Matt. And what you've got there is and no comment here, but the graphics were not quite, yes, Joe? 1995. Yeah, Mitchell et al. 1995. And slightly mid-1990s graphics, if I dare say so, but the dotted line there is the observed global average observed temperature. The dashed line is a simulation of the model, just including increasing greenhouse gas concentrations. And one of the key things that John Mitchell and his colleagues from the Hadley Centre realised, that you also need to take account not just of the greenhouse gases, but also the effects of sulfate aerosols. So the effect of air pollution putting sulfur dioxide into the atmosphere and then producing sulfate aerosols that reflect solar radiation directly and also can make clouds more reflective as well. And when they included both of those effects into the climate model, then this was the first climate model that was simulating something that looked broadly consistent with what was observed. So this was an important step, because now we'd moved beyond the sort of old style experiments where you might, for example, double CO2 in a model and look at the overall warming and think about the climate sensitivity. This was an experiment where we were trying to, or John and his colleagues were trying to actually simulate what had actually happened. And the mid-1990s were also a particularly, it was a particularly time for this whole topic of understanding the causes of climate change. And I want to particularly note here the contributions of two scientists, Gabi Hegel and Ben Santer, who were both postdoctoral researchers with Klaus Hasselmann, who's the other recipient of the Nobel Prize in Physics, alongside Manabe, I was referred to just before. So they both worked under Klaus Hasselmann. Klaus Hasselmann had developed a new technique called optimal detection for basically for detecting signals in a noisy background, which is basically what we're doing here. We're trying to detect whether or not we're seeing something significant in the noisy background of climate variability that, of course, we've heard about earlier today. And this, Professor Gabi Hegel, now based up in Edinburgh, then, as I say, she was working with Klaus Hasselmann in Germany in the Max Planck Institute. And this is the graph taken actually from the IPCC report, the second assessment report, showing what the global average temperature curve looked like at that time. And just looking into this now, it's quite striking to me that the features in that leap out, to me certainly, are not particularly the overall warming. It's obviously warmer at the end than it is at the start, but there's some features in there, notably the early century warming. There's a period when there's not so much warming, and then starting in the late 1970s or so, there's a period of further warming. What Gabi did was she used Klaus Hasselmann's signal-to-noise detection techniques to see whether or not the models were simulating something that was becoming increasingly correlated with what the observational temperature pattern at the surface was. Now, in parallel to so Ben, who'd preceded Gabi as a postdoc, he'd then gone over to the United States and was working at what's called the Lawrence Livermore National Laboratory, and he had started looking at the vertical pattern of change, temperature change, from the surface up through the depth of the atmosphere, up through the troposphere, up into the stratosphere. And this plot is taken from his seminal paper in Nature in 1996, and it's showing the pattern of observed temperature change as measured by weather balloons as a trend. So where you've got the yellows and oranges and reds, that's a warming trend. Where you've got the blues and the purples, that's a cooling trend. And we're going from the high northern latitudes at the left to the high southern latitudes at the right. And then we're going up through the depth of the atmosphere. And again, this has got a fascinating pattern within it. And this is a distinctive, what you can call a fingerprint of climate change, because what we're seeing here is a warming of the troposphere and a cooling of the stratosphere. And reference the physical processes that we talked about so far today. This is consistent with the effects of both greenhouse gases, increases in the atmosphere, which would cause a warming troposphere and a cooling stratosphere, but also the effects of stratospheric ozone depletion, notably the ozone hole in the above the South Pole, which is where you've got that purple, very strong cooling. But another feature that's really important here as well, and it's back to the sulfate aerosols, is that there is more warming in the southern hemisphere than there is in the northern hemisphere. And what Ben did was he ran the models at that time that he had with all of these different factors, the increasing greenhouse gas concentrations, the sulfate aerosols, including the stratospheric ozone depletion. And he looked at all these patterns and he showed that the degree of agreement between the observational pattern of temperature change in these model fingerprints was significant and attributable to the effects of human activities, being well outside the range that could be expected to have happened by just natural processes. So with this work, the Mitchell et al. 95 paper, the Santer et al., the Hegel et al. Papers in particular, all of this evidence had come through in time for the second assessment report of the IPCC in 1996, which came up with this very striking conclusion at the time that the balance of evidence suggests a discernible human influence on global climate. This was the first time that the IPCC had made such a statement explicitly linking human activities to changes in climate. And as I discussed in more length in my book than I'm going to go into now in this presentation, this was also the time when there was a strong backlash, or particularly rise in a backlash by the climate change denial, in effect, not just to try to dispute the science, but also to attack the scientists, in this case, Ben Santer, accusing him of, as it says there, a major deception of global warming through allegedly distorting the IPCC process, which was very much not the case. But it's an indication of how this science, and in particular the science around the detection and attribution of climate change, was a politicized or a science that was prone to being attacked for political reasons because of the important implications of the scientific conclusions that significant changes were afoot and could be attributable to human activities. Matt already showed this picture, but didn't say much about it, so I will say a little bit more about this. Matt is on this picture, as am I, somewhere sneaking around at the back, as is Joe, as is, I can't remember whether you're on this up there, Keith. Yes, I think you're on there, aren't you, Keith? And the front left there is Klaus Hasselmann. This was a meeting organised by John Mitchell with Simon Tett in April 1998 in the old Hadley Centre. This is when we used to be in Bracknell. And you know, this was quite a remarkable meeting, actually, I think, looking back, because we basically convened just about everybody at that time who had a strong interest in this area. I think it's also interesting to look back and realize that we could all fit in on that picture. So although this science was hugely significant, you know, it wasn't done by thousands of people. It was done by, you know, all those people in the room, basically. So yes, so now we go on to the next significant moment, at least in my history, as I'm recounting it today, which is science that I was very closely involved in, thanks to the fact that I was now working with John in his group and Simon Tett and William Ingram. This was another step forward in our terms of our modelling and our simulation of past climate, because now we had the HADCM3 model that you heard about from Matt, and we had, and thanks very much to John, who was able to arrange it so that we had basically access to a huge percentage of the computing power at that time, to run these experiments in which we didn't just project into the future, but we sought to do hindcasts of the past. So the red curves there are the observational, the global average temperatures again, and we have three graphs there, which are experiments that we did in which we, so on the top left there you've got, so the grey bands are ensembles of 4 simulations, because that's basically all we could afford to do at that time. So we had ensembles of 4 simulations, all of which had different initial conditions, but which had identical climate forcings. That means that they had, in this case, for the top left, they had the effects of explosive volcanic eruptions. They also had changes in solar output. And then they had all the emergent processes that you heard about from Matt. El Niños, for example, La Niñas came and went in the model, etc., as emergent processes in the model. You can see that the grey band, the model simulations, do not simulate the recent warming or anything like it. If you go to the top right, we now have simulations which actually now don't include those natural forcings I talked about, like volcanoes and solar forcing, but they do now include increasing greenhouse gas concentrations in the atmosphere. They do include, crucially, the effects of sulfate aerosols I talked about. Now you can see that those models do simulate the more recent warming, but they don't do such a great job at simulating the early 20th century warming. And then we did this further set of simulations that I was put in charge of making, which include all of these forcings together. And now you can see that they do this remarkably good simulation of what was actually happening. Put that whole story together, you can see that we have a comprehensive explanation now, not just of more recent warming, but also the earlier evolution of global temperatures since we had the global records. And that then led the IPCC conclusion in the third assessment report to conclude that most of the observed warming is likely to have been due to the increase in greenhouse gas concentrations. If we go forward now to the next IPCC report, the fourth assessment report of 2007, which is when now I was a lead author on that report. Now we had more evidence, because now what we were starting to be able to do now, using the techniques that Hasselmann had originally originated, and then that then a group in the UK, Miles Allen, Simon Tett, myself, John Mitchell, had developed, which was now what we were able to do was to use this type of fingerprinting technology and start to quantify how much of the observed warming was attributable to the different factors. And splitting that up in this graph into contributions due to the increasing greenhouse gases in red, that's a warming, cooling due to the effects of sulfate aerosols in the green, and then the blue bars are the effects of natural forcings. And now, this is a figure taken from the IPCC report, the fourth assessment report. We have a number of different estimates there. So we're now not just using Hadsium-3, we're using a range of different models, including, for example, Japanese, American models. And therefore we can do a synthesis. So we can fold in now modeling uncertainty into this, as well as some methodological uncertainty. And that additional level of information and additional level of confidence allowed us to say in that IPCC report is to increase the level of confidence and now to talk about the idea that the observed increase in global average temperature since the mid-20th century is very likely due to the observed increase in greenhouse gas concentrations. We're using IPCC calibrated language. So likely in the third assessment report meant that it was at least a 66% chance of the statement being correct. Now we've increased that to at least a 90% chance using this IPCC calibrated language. Why could we not go further? And this was a very vigorous, and I was also rigorous, debate at the plenary meeting in Paris for this assessment that I was engaged in with the government. Why could we not go further? Well, there was an important piece of uncertainty that remained at this point, which is to do with how the oceans were warming up. And this graph is taken from the fourth assessment report, and it's showing an estimate of ocean heat content from the surface to 700 meters below the surface. And at this time, we had these representations of the change in ocean heat content, which, as a first principles you would expect would be gradually increasing due to the effects of the warming. This was not the case because in the mid-80s, it looked like there was, and particularly from the mid-80s, there was a rather sharp cooling, apparently, of ocean temperatures. And the fact that there should be this variability in ocean temperatures caused us to have some pause about our attribution statement, because if there was some larger amount of variability in the reality than was simulated by our models, then that would lead us to think that we needed to be a bit careful about the overall level of confidence. Now, we had some reasons to think there might be some issues with this observational data set, but we didn't know at that point. And also it allows me to make a very important point about all of this work, is that it does depend on models, because we use models to provide estimates of the variability of the climate system, the internal variability of the climate system. We can run our models for many, many centuries, and therefore we can see whether the century scale warming that's been observed is significant compared to what we would expect from just natural internal variability, where there would be no net warming. So therefore, when we see observational data that apparently in some sense contradicts what we're seeing in models, then we need to tread with a little bit of caution. Now, at that point, we did have some suspicions that there could be something, some observational artifact affecting this data set, but we didn't know at that point until the reassessments were made. Actually, were just being made round about the time, actually, of the fourth assessment report in 2007. But by the time we got to the fifth assessment report of 2013, we had reassessments of the ocean heat content change. And to cut a long and I think rather fascinating story short, you've got to remember that before 2000 or so, when we had the Argo floats that were giving us a very comprehensive estimate of ocean temperatures, before that we were reliant on a whole load of different types of data source, notably the expendable bathythermographs, which are basically instruments that go down on wires, and therefore the temperature, the location below the depth of the sea surface is based on the inferring where it is from the speed of fall of that instrument down this wire. And technical issues due to that had affected the observational records before that point, which makes a point, I suppose, that when we think about these assessments, we need to think not just, of course, about the modelling uncertainty and the issues in the models, but also the observational uncertainty and the potential issues in the model in the observational data set. Anyway, at the fifth assessment report, because we'd now cleared up the issue with the ocean heat content, we could now increase our level of uncertainty and now increase it to it's extremely likely that the dominant cause of the observed warming since the mid-20th century is anthropogenic. And these types of bars which quantify the warming into the different contributions was now based on a much more comprehensive set of models. We're now into the era of the CMIP ensembles that Matt was talking about, CMIP 5 ensemble in this case. So if we go forward to the most recent IPCC report of the sixth assessment report, which was released in August last year, you will see that the conclusion related to the causes is now expressed in a rather different way, but it's now talking about basically being unequivocal that human influence is behind the warming. We have a much larger range of models, and this plot on the right there shows the spatial pattern of temperature change. So relating to what Tim was talking about, you can see the greater warming over land and ocean. You can see the greater warming at high latitudes as well, and these are based on this is the basic fingerprint based on well understood physical processes, which give us again greater confidence in this conclusion. I was going to very briefly mention the whole topic of event attribution without going into this in great detail, but we are now being able to use this sort of science to make conclusions about specific episodes in our evolution of our climate. And this one was to do with the prolonged Siberian heat wave, whereby temperatures were elevated in Siberia from January to June for a significant period of time. And we used the same type of approach of ensembles of simulations that include anthropogenic forcings and ensembles of simulations that exclude those and just have natural factors, basically to work out what are the odds that you would see, for example, in this case, really elevated Siberian temperatures for such a long period of time. And now we are starting to see when we make this sort of calculation that it is effectively impossible that you would see such temperatures without climate change. And this type of science is getting prominence in the media, as I make the point there, and makes us think about future. Very quickly then onto the future, just a couple of points to make there. This is from the AR6 report looking at the future global average temperature change according to different scenarios of emissions, but related to the question, and we've already seen from, I think, Matt's presentation that the past simulations made by previous generations of modelers have been consistent with what we've observed since. And then I also just very quickly wanted to make the point that these patterns of change, at least in terms of temperature, are very consistent with what we were predicting back in the mid-1990s. And that's taken from work that we took to Kyoto back in 1997. So just to finish then, and hopefully perhaps look forward to some of the presentations coming up later, so that if some of the basic science has effectively remained the same for the last 20 or 30 years, I think one of the areas in which the science has certainly advanced dramatically is in terms also of the risks of climate change and what this means regionally, which is already touched on by Matt. So one aspect of this I want to highlight, where the information has certainly changed a lot in AR6 compared to previous reports, is looking at sea level rise. If this is estimates of sea level rise going forward over the next century, but you'll see there a curve that says, in some sense, sort of plausible worst case scenario in terms of if there are dynamic changes in the ice sheets. And if you, in the IPCC report, you'll see this graph, which shows what the potential sea level rise could be out to 2300, up to 15 meters of sea level rise, if some of these dynamical processes kick in and if we have some of the upper level of emissions changes. So this is the sort of information that's now being framed in a way that can be used for risk management. I'll stop there. Thank you.
My understanding is that David Borlow's recorded talk will be slightly shorter than advertised, so I propose we break for refreshments at 15:45 and start at 16:05. So there is time for perhaps a couple of questions Peter. Tim.
Thank you. So the optimal detection type things you mentioned at the start, they always seem a bit of a black box sometimes. So as a communication tool, do you think the results from AR3 that you showed, where you can just visually see the agreement between the models when you have all the forcings in and the disagreement when the natural forcings are there, is that a better approach, do you think, for communicating this?
Yeah, I think it probably is, and I think that's why that figure was so important at the time. Actually, I mean, it was quite I justified a little personal reminiscence at that point, as I recall it, and John was there too, of course. You know, we only had the one model, and those results came in super late for the inclusion in that report, and getting those through peer review was just done by the skin of our teeth. And there was only the one model at that time. There was supporting evidence behind it as well. But I sometimes wonder whether with the later IPCC processes that would have perhaps not necessarily have got through at that time, you know, because of the point about needing supporting lines of evidence, etc. But that's just me speculating a little bit there. But that figure certainly had big power and communication value, I think, and perhaps even more than perhaps the scientists realized at the time, because we were actually a bit reluctant to do those initially. At any rate, we were a bit reluctant to do those simulations where we included all the forcings together, because there was an argument to be made that with the simulations with just anthropogenic forcings and just natural forcings, we could then crunch it together with our optimal detection procedures like you've talked about and produce our derived products. As you say, there is a technical black boxishness to that it's a robust method and it's been proved to be so, but for communication, I think we demonstrated back in AR3 the power, as you say, the power of that. And if you look fast forward to AR6 from the most recent report came out last year, you'll see that they've got the same type of presentation updated to present with many, many more models and snazzier graphics and all that. So yeah, I agree. It's a powerful tool.
Time for one more question.
Thanks, Peter. Great talk. I'm going to go out and buy your book.
I've got one. You can
Right,
sell it.
Do you take credit cards?
Yes, I do actually.
So in that context, we know the deniers haven't gone away, and indeed we have Nigel Farage now with his new Net Zero Watch activity. And I'm just wondering what your opinion is on what scientists should or shouldn't do to respond to that. I mean, could we just ignore it, or should we be all guns blazing, saying what's wrong with it? I mean, they don't listen though, do they?
Well, just nice, easy question, Jay, but thank you. No, we shouldn't. We definitely shouldn't ignore it. And I was actually asked by The Guardian to watch, we were chatting over tea about this, of course, but I was asked to watch The Guardian, the Global Warming Policy Foundation annual lecture by somebody called Steve Koonin, and I wouldn't have watched this otherwise. And I did watch it, and I found it a real eye-opener, which, you may be interested in as well if you haven't watched it, in that the arguments that he provides in 2021 with, members of the Net Zero Scrutiny Group like Lily and the other person I can't remember his name of, there in the audience, will be very, very familiar to all of you out there, right? So first of all, cherry picking his data points, and having some favourite bit of graph that you don't really know the provenance of, but from which he claims that, some heat wave in 2020 is no different than it was in 1930, claiming that the IPCC report doesn't say what people say that the IPCC report says, which is a long-standing argument from many years ago, but which is still being used to this day, despite the fact, I was in Glasgow and I heard Valerie Massel-Delmotte and her colleagues talking about their own report in the most robust terms, which is written, in the most robust terms. And I think it's a very good communication piece, by the way, R6. That's the second argument. Third argument, of course, is using uncertainties to argue that, and, Koonin has gone through the whole report very carefully and picked out one or two phrases where there's a bit of uncertainty about, or a certain amount of uncertainty about tropical cyclones, for example, blown that whole thing out of proportion to support an argument that we don't need to worry about 5 degrees global warming because it will just knock a few % off GDP at worst. And therefore we should just, to use his words, sit back and relax and, wait for a few years and we'll be able to adapt. So I wouldn't have known what was in that lecture if I hadn't gone to watch it. I think it's useful that you all know that this this net zero scrutiny group and the GWF, etc., are still leveraging off the same old arguments in effect. There's nothing really new there, but of course they're using the moment of rising gas prices, etc., to argue that we should sit back and relax, to use Koenig's expression, on this whole topic. So yes, I think there is a role we can play, because it's still, these arguments still rely to quite a large extent actually on the sort of science that we do in this room. So I think we should be saying our bit as and when. Yeah.
The last talk before cup of tea time is from Jason Lowe, Dr. Jason Lowe, who leads the interaction in the Hadley Centre and with other people at the universities on policy with the UK government and the science that's being developed. And the talk is Provision of Climate Science for Policy Advice from the UK Science Community. Jason.
Thanks, Chris. Just listening to Matt, I was thinking about my first day in the Hadley Centre.
Same day.
We did overlap. We were in H210, I remember, the same office for a spell. And Gabby Hegel was actually visiting at the time, which was quite exciting. But I turned up on the first day and I knew I'd be looking at sea level rise. And I sat down with Jonathan Gregory and we talked about sea level rise, and he said you'll be focusing on the spatial pattern of sea level rise. And then I went a bit further down the corridor and John told me all about HADCM2 and said, of course, the ocean, it has a rigid lid, so it's flat. So if you're looking at the spatial pattern of sea level rise, that's going to be quite a challenge. But it was an exciting time. As you say, I think there were lots going on. I really struggled to decide what to present in this talk. So I thought, shall I go down a UK focus? Shall I focus on the science we've done around providing input towards the UK carbon budgets? Shall we try and look at the very early UK CPs and UK SIPs? I managed to track down the brochure from the first one in 1998, which is a mere 98 pages long compared with the 1,000 or so we have in UK CP18 in total. What I decided on was to focus on the international issue, and in particular, informing the global temperature and mitigation targets we see in the United Nations framework. I'll start with a timeline. I don't know how well you can see that. At the left-hand side, we've got here the Rio Earth Summit when the framework convention was really born. And that helped us understand the overall goal of attempting to avoid dangerous anthropogenic climate change, and to do so at a rate that would allow ecosystems to adapt. It didn't tell us what dangerous climate change was at that time. A great deal of research has focused on really trying to understand the consequences. As you come forward in time, I've picked off a few of the COPs. So COP3 was particularly significant. COP3 was when the Kyoto Protocol was agreed. And there were some people in this room who were at that COP. It was a little before my time. But to have a global agreement that committed nations to reducing their greenhouse gas emissions, it was an amazing step forward. And I remember the publicity around it. Come forward to COP15, Copenhagen Accord. And I remember that year building up to it. So earlier in the year, there was it was a G7 communication that really made a very strong statement around limiting warming to below 2 degrees above pre-industrial levels. And there was the assumption it would find its way into the text of the Copenhagen Agreement, and there'd be a new framework for reducing emissions. That didn't happen. So in some ways, COP15 was the COP that everyone expected so much of, but it just didn't materialize. The following year, there was an attempt to pick up some of the pieces of COP and actually get the temperature target into the negotiating text, which did happen. And then there was this period down here of the structured expert dialogue. That was building up to what really was the big change at COP21. So COP21 was where the language changed around the long-term target. Now we're trying to stay well below 2 degrees and pursue efforts to limit below 1.5 degrees of warming. And it also introduced the concept of the nationally determined contributions. So countries listing their own voluntary pledge towards emission reductions. And then the idea was 5 years later, they would be reviewed. So that's why COP26 in some ways was such an important one, because it was pushed back a year. I think a lot of the material around COP26 focused on the idea of, is 1.5 degrees still alive as a target? And we'll come to that later in the talk. But it actually did more than that. So it brought forward the next review of the NDCs. They'll have to be presented again this year in 2022 in Egypt. But it also put much more focus on adaptation and thinking about how do we promote adaptation, how do we finance adaptation. And there were some really exciting events around the main COP negotiations, such as the pledge for methane reductions and the GFANZ group trying to mobilize private finance. And there were some very interesting words around the $130 trillion of private finance. How effective that will be and how much of that is new money and how much of it will be steered remains to be seen. I wanted to put the IPCC covers at both ends. So it's at the right-hand end, the new report, but really the birth of the IPCC is at the first point on here in 1988. And thinking about the science of mitigation, it's so tied to IPCC and the development over that period. So I'm going to show particular results from the Met Office and UK community, but they are intertwined with the IPCC process, and many of them have found their way into IPCC. And I also wanted to put this plot up. I put this in yesterday just to reflect that if we look along the same time axis as I pulled out for some of those years, I haven't got emissions for 2021 yet, so I've only gone to the end of 2019. But you can see as we go through this period from the Rio Earth Summit, the global emissions of carbon dioxide have been rising significantly. And on the right-hand side, we talk increasingly about a carbon budget that corresponds to a given warming level. Here I'm picking the 1.5 degree carbon budget. We didn't talk in those terms, to be fair, in 1992. But if we had, well, we would have had about 50% of it left at that point. Now we're down to about 85% of it being used up. That's just a reflection on what's been happening while the negotiations have been going on. Now let's move to the science. We've already heard from Peter this paper on the left that comes from the HADCM2 model simulations in 1995. This early period was very much focusing on trying to characterize how big the change would be and to develop the models that allowed us to do that in a credible way. So I included this here because of the inclusion of aerosols, or at least the direct effect of aerosols in this particular simulation. And the fact that it's taking us closer to something that in process terms matches the real climate system. On the right-hand side, we've got the Cox et al. Paper that has been mentioned a few times. From these early papers, you can tell when a paper is really important because the Met Office was able to splash out on colour plots, and you could have the lines in colour, so you know that really marks out a step. But what Peter did was include the representation of the carbon cycle. And so in the forward climate simulations, we could include climate carbon cycle feedback. And you can see here the enhancement in atmospheric CO2 concentration when you have a case where you don't include this feedback compared to when you do, driven by the same pathway of emissions. So it's amplifying the concentration of CO2 and it amplifies the warming as well. And that made a major impact at the UNFCCC conference and party event for that year. I remember there was a real buzz around this paper, and it was finding its way into discussion by some of the negotiators. Still in this period, we started to think about more policy or mitigation relevant simulations. This is another paper led by John from 2000. And here we ran the so-called S750 and S550 mitigation scenarios. It was compared with this scenario here, which is labeled as a baseline, but at the time we routinely referred to these as business as usual, and they always went up. Thankfully, we don't do that now, and business as usual is not a rising steep emissions and temperature curve like this. And I think it's important when we think of the language that we have come off this curve. These early simulations, the lowest one, the 550, which was CO2 equivalent, you see here it's giving a warming that's well above the 2 degree level, even for a moderate climate sensitivity model. We didn't only use the really complex models. So we did have the model with a million lines of code, but we also had simple climate models, which were really useful for running large numbers of cases and looking at other aspects of uncertainty in global average response. This particular plot, which I really had to hunt around for, I remembered it. It was actually run with a model that Peter Rowntree wrote. The basis of which actually still exists within UKCP as a simple model that was developed later by others. But this is kind of reflecting that we're trying to address the needs that we're hearing from our stakeholders in government, from DEFRA and from DEC at the time, later to become BEIS. And you can see the small but noticeable effect that implementing Kyoto has on the global temperature. So it's a first step. So then we come forward. So now I'm in the 2005 to 2009 period. And the policy advice from climate science is starting to become more multidisciplinary. I'm using the term multidisciplinary because we're thinking in lots of disciplines, but they're not working together very effectively yet. And one of the highlights in this period was the Avoiding Dangerous Climate Change conference in 2005. I remember we had it not that long after the Met Office had moved to Exeter. It was opened by Margaret Beckett, who was Secretary of State for the Environment at the time. And there were sessions that covered the physical climate science, climate impacts, and climate mitigation and technology. So it really was an attempt to bring expertise together. Looking at the list today, when you go and look at the list of uncertainty associated with that.
Stopped working, I'm not sure.
I thought I heard it go quiet. Thank you. So Chris Rapley gave what at the time I think was a very scary discussion of how the Antarctic might contribute to sea level rise. And there was a lot of media attention around that. Perhaps one of the most policy relevant aspects, though, was the recognition of giving a high likelihood of staying below 2 degrees would mean stabilizing atmospheric concentrations quite a bit below the 550 parts per million level, and actually going down to below 450 parts per million. It still worried me a lot, certainly, that we were talking in terms of the atmospheric concentrations rather than the emissions. So the final component of the conference that focused on the emissions and the types of technology, which we were already seeing being implemented, and the price is starting to come down for solar photovoltaic and some of the wind technologies. This conference really did inform the climate debate. I think it also informed some of the thinking around the UK's Climate Change Act and the need for that. Maybe that will come out in the panel discussion later. The other thing that happened in this intermediate period was the rise of the global carbon budget. So there were several studies that came out at very similar time. So Miles Allen led this particular study that several of us were on around the idea of the trillionth ton. And what this is about is when you plot the cumulative emissions of carbon dioxide along one axis and the peak warming along the other, what you find is the relationship is actually quite straight. And there are good physical reasons for that to do with the balance of heat uptake and carbon uptake. But you can use that to say, well, okay, if I've got a temperature target, in this case of 2 degrees, what does that mean in terms of an emission target? And that's where the idea of the trillionth ton came from. At the same time Miles was writing this paper, there was a second paper concluding something very similar by Malte Meinshausen, and a third by Damon Matthews. So we were all having these similar ideas around carbon budgets, global carbon budgets. Certainly the IPCC report since then, if ever mitigation is talked about, there is a variant of the carbon emissions against warming paper with our ability to quantify that carbon budget improving over time. So now I'm stepping forward into the avoid period of UK climate science for policy advice. And this was an attempt to really start to become interdisciplinary, to bring together those focusing on impacts with the physical scientists, with the specialists on energy, with the economists. And what we tried to do was bring together the Met Office Hadley Centre with the Walker Institute at Reading, the Tyndall Centre at UEA, and the Grantham Institute at Imperial. And I can see Simon Buckle in the audience as well. He was there on the day the Avoid project was born and made a major contribution to the Avoid project, as did Nigel Arnell and Rachel Warren, to name two of the other leads. And one of the iconic outputs is this plot over here. This was an attempt to say, well, at various levels of global warming, what are the impacts? And you can see these are really quite scary numbers when you look at number of people affected by heat waves or water stress or flooding. And the idea was to improve the estimate of these values, but also reframe the problem in terms of the avoided impacts and really focus on the benefits of mitigation. And in this case, going from the 4.5 degree world down to the 2 degree world, you could avoid somewhere between 87 and 23% of the impacts at the higher warming level. Work published since then tells us if you go from the 2 degrees to the 1.5 degree target, then using similar techniques, you can avoid somewhere between an extra 25 and 60% of the impacts. We also fed the results of the Avoid programme into various international activities. So the one on the left is a European report after Copenhagen that tried to pull together some of the scientific evidence on the feasibility of meeting these lower warming levels. And the one on the right is the very first of the emission gap reports, which is still published today, and on a yearly basis try to focus and highlight the difference between the pathway we're on and the pathway that is compatible with a 1.5 degree future. There is another infographic which, thinking about it, I probably should have added on the economic benefit of early action, which I think was one of the key results that came out of the Grantham Institute. And Simon and also AJ Gambier worked very hard on producing that. These are a couple of the exciting results as well. So we're in this period, and we're in a position where it clearly looks like it's going to be quite difficult to limit warming to below 2 degrees. And the debate really started to include this idea of carbon dioxide removal, or negative emissions, if you want to call it that. It was based on a number of thinking about how one might do this around year 2000, and started to appear in scenarios a few years later, as Azar et al. Shows. But it opens up additional flexibility. So one of the questions in Avoid was really focusing on the idea of when do you need to peak and how much flexibility is there on the year. And this plot, so-called blob plot, it involved running simple version of the climate model tuned to the more complex models that Matt showed, and also trying to better represent the observed record, and running it forward with, I think there were around 100,000 simulations went into this particular case, each with a slightly different view of what the emissions might be like in the future. And you can read off here. So this is a one for 50% chance of being below 2 degrees in 2100. So if you put this line that was sort of coming out of the discussions on the technology, the annual reduction rates beyond 3.5% per year would be very difficult to achieve, may even be infeasible in terms of what we thought certainly at that time. So you need to be below this line. If you don't want any negative emissions or carbon dioxide removal, you need to be on the left of this line. So you're in this space of the blue dots. But the idea of negative emissions of different sizes, it opens up that flexibility a little bit, either in terms of the peaking year or in terms of the rate at which you need to reduce emissions. But we had a real concern about this. When you looked in the IPCC database across the estimates they'd made with integrated assessment models, some of the numbers were absolutely enormous in terms of the amount of carbon dioxide that was being removed. It's this section here. So one of the other results in Avoid that Andy Wiltshire led on was trying to get a better constraint on this. So thinking about what was on the land before you used it for biofuels, which you then put into your carbon capture and storage, and also including physical effects like the albedo of different land surface types. And that result showed, well, the potential for negative emissions, it certainly still existed, but it may not be anywhere near as optimistic as we were seeing in the IPCC at the time. So we were able to feed this into the policy debate as it happened, and being able to do that on a fairly short turnaround was a real advantage. So we had to stay rooted in IPCC science, but we could update some of the thinking and tailor it to the questions that were being asked on an annual or more frequent basis. Then along came Paris in 2021, and the focus very much shifted to 1.5 degrees. It also has, when you delve into the Paris text, really interesting statements around net zero. And it also has some very detailed text around adaptation. But for our mitigation story, it moved us on to thinking about 1.5 degrees. And looking on the left are a set of emissions from the SR 1.5 database of emissions. And each one of these represents a future from an integrated assessment model. They vary in terms of assumptions around policy, technology, population growth, wealth, etc. And we've coloured the ones in green that limit warming to below 1.5 with a 50% chance. And you can see almost all of them have got this sizable negative emissions and a very, very rapid reduction in this period in the 2020s. If we put the NDC, the places on here, they'd be around here. And so they sit somewhere above the 1.5 degree pathways. On the right hand side, I won't dwell on this, but you can actually pull out many different 1.5 degree worlds. They have different total primary energy needs. They have a different balance of technology. And that's really important because it means in some countries, in some nations, particular measures may be more suitable, more feasible than others. And I think this was a very valuable message to get across. Moving forward to COP26, we can actually say, is 1.5 degrees still alive? there are certainly scenarios in the SR 1.5 database that correspond to the emission pledges that bring you down after an overshoot to 1.5 in 2100, but they all have an overshoot. So it's on the margin of being feasible depending on how you interpret it. And you can see these overshoot scenarios in red on this temperature versus time plot. So I'm going to finish with my final slide looking into the future. So the science, I think we've heard from several of the speakers, needs to focus much more on solutions in this phase. And for emission reduction, there are several things it needs to do. So it still needs to contribute to improving our understanding of targets, narrowing the uncertainty in the carbon budgets, and better understanding and quantifying the impacts at different warming levels. But we also need to monitor. We need to use our models in a cleverer way with observations to understand how well we're doing, including understanding the reductions in greenhouse gases, where they're happening and where they're not. We also need to use our science and models to contribute to mitigation approaches, and that requires a better understanding on a regional basis of the carbon sinks and how to protect those. It also means that we can use our models, often in weather forecast mode, to achieve better operations, for instance, of energy networks or planning our low carbon transportation. We can look at side effects with the models, for instance, of novel aviation fuels because we have chemistry in them. But we also need to remember that it's not just about the emission reduction. It has to be a resilient low carbon future. And this is where we have to get down to very fine spatial scales and look at place-based impacts and test solutions that make our future more resilient. That's my final slide, but I couldn't resist on my thank you slide. Every COP brochure the Met Office has produced that I could get my hands on, I've got the cover on here. I couldn't get the ones prior to 2003, but thanks to Nick Hopkins for helping me assemble these ones. Thank you.
Time for one very brief question. One question. No, Joshua.
Hang on, try without the mic because it's got the feedback thing. So you had the graph where you had the. You had the graph with the what happened with the Kyoto and the potential improvements Kyoto gave. I just wondered with COP26 one in Glasgow and the potential improvements we got there, so the phase down of coal, not a phase out but a phase down, and I know it's not part of Kyoto, but the EU banning for fossil fuel cars by 2030, that sort of thing. Would you say, have a similar impact to Kyoto, or is it not really enough to tell at the moment where the COP26 have a sort of lasting beneficial impact?
So if we take the pledges that are in COP26 and that are an evolution of what came earlier, if one takes the emissions through those pledges, but then levels out the emissions, it's very close to the idea of a current policy. That gives us a median estimate of around 2.5 to 3 degrees of warming relative to pre-industrial. So it's bringing us quite a long way below those very high emission scenarios that would go up to 4.5 or 5 degrees, but it's still quite a long way above 1.5. If we include the most optimistic announcements, which are not necessarily coming with a plan and which are not always in policy terms and not in legislation, then there's some great evidence plotted up by Carbon Brief that highlights that can actually bring us down to of the order of 2 degrees or maybe even a little bit below 2 degrees. But remember, those are just announcements. So there's definite progress beyond that Kyoto plot, but not as far as perhaps we need to go if we want to limit warming to those lowest levels and avoid the impacts.
Okay. Okay. Back at 4:05 if you can possibly make it. Thank you. Okay, everybody. We better make a start on this final session, and I've been asked to point out to those online, and I think there are about 65 online. Please, if you have a question, please go to the chat room, and the Royal Met Soc staff will be able to extract questions asked soon enough, and I can use one or two of them at the end of the next two talks. So the first talk this afternoon will be from Professor Richard Betts, who's Met Office and Exeter University, very much Met Office expert on adaptation to climate change. How can society adapt to climate change? Examples from history, the present, and likely near future. Richard.
Is it working? No, I don't think so. Use this one, yeah? Oh, this is on? Yeah. Okay. Right. Thank you. Yeah. Thank you, Chris. So yeah, I took advantage of the 2-year delay in this meeting to put together a talk which with a lot of material which didn't even exist 2 years ago. In fact, I've taken the opportunity to present some of the conclusions from the IPCC Sixth Assessment Working Group 2 report, which came out last week, which I was very much involved in. So that's got hot off the press, but I'll also put that in context of some of the earlier IPCC reports and how some of the concepts have developed over time. I'll also talk about some of the conclusions from the UK Climate Change Risk Assessment, which came out last year, which again I was very much involved in. So I've put these two things together to give a very up-to-date talk. So on the topic of adaptation, this is a photo from Dawlish in Devon, the famous railway line that fell into the sea in some storms about a decade or so ago, and has now been upgraded. The sea wall it was first rebuilt in its original form and has now been upgraded to cope with higher sea levels now and in the future, to give a stronger level of defence for the station and the town behind us. So this is climate change adaptation in action. You can see they call it the wave crawler machine there building this new sea wall. The first question is, why do we need to adapt to climate change? Aren't we just trying to avoid it? Well, of course, climate change is already with us and is already having impacts. This is the first headline statement from last week's IPCC report, actually. Peter earlier on talked about the development and the evolution of the attribution statements from the Working Group 1 report on the strength of confidence in the human cause of climate change. These kind of attribution statements are now possible on the impacts side as well. Last week, the summary for policymakers from the Working Group 2 report says that human-induced climate change, including more frequent and intense extreme events, that's an important part of this, has caused widespread adverse impacts and related losses and damages to nature and people beyond natural climate variability. So not only is there an attribution of impacts to observed climate change, there's also an attribution to human-caused climate change in many areas. And this is one of the key figures behind that, a very technical figure which needs looking at in more detail, so I encourage you to go and look at the report itself. But just to highlight, just to talk about roughly what the key message it's trying to bring across. It's assessing for all the regions of the world at the continental scale, largely, and globally, the sign of the impact for various sectors to do with water and food, aspects of human health and well-being, and impacts on cities, settlements, and infrastructure. And the negative sign means an increasing adverse impact, so a bad impact. The plus-minus sign means there's a mixture of positive and adverse impacts in those regions. There would have been a positive sign if there'd been any evidence that at the regional scale there was any overall positive impacts, but there were none found in the literature. So the big picture story is that we are seeing at least mixed signs of impacts, but largely adverse impacts of observed climate change, much of which is due to human causes, as I've said, with a range of levels of confidence communicated by the depth of the colours here, but in many cases it's high or very high confidence in the dark colours. So we're seeing these impacts across the world. And of course, some further climate change is inevitable. A version of this figure has already been shown, but this is the projected global warming for the remainder of this century, following the observed climate change on the black line on the left part of the plot, the future change under different scenarios, different levels of buildup of greenhouse gases and aerosols in the atmosphere under different assumptions relating to different emission scenarios, ranging from very high rates of buildup leading to 4 degrees or above global warming by the end of the century, down to scenarios which slightly overshoot 1.5 degrees in the midterm and then come down below that. If there's very rapid and deep global emissions cuts starting immediately, with CO2 emissions globally halving within 10 years and reaching net zero roughly mid-century. So the very low scenario would need that. So even with that very low scenario, we have some level of warming in the pipeline, even if we meet the Paris Agreement targets of limiting warming to well below 2 degrees. So we do need to adapt to some further change as well as the change which is already underway. Some concepts that relate to climate change adaptation. We've heard a lot about the physical climate science, of course. This is the Royal Meteorological Society. Many of us are meteorologists, of course, but not everyone. But the human dimension is very important as well, as has been mentioned in some of the earlier talks. And I'll bring some of that in. You can categorize adaptation in several different ways, but one of the broad different categories is whether adaptation is reactive, so it happens after the fact in response to changes that are happening, or anticipatory, so it's happening beforehand. This is the terminology that was used in the IPCC third assessment report in 2001. So for natural systems don't adapt in advance. It's always reactive, but it's things like changes in the length of the growing season, so springtime events happening earlier, like trees coming to leaf earlier under warmer temperatures and so on, changes in ecosystem composition, shifts in various positions of various ecosystems like wetlands and so on in response to rising sea levels. But human systems, both in the public and private sector, can respond and adapt either reactively or in anticipation of future changes. I thought it was interesting, actually, the 2001 report talked about redesign of oil rigs as a climate change adaptation. That's kind of ironic. But it was, yeah, different ways of framing and thinking about adaptation. And of course, we're trying to encourage much more adaptation in advance rather than simply reactively. And that's one of the main roles of climate science, of course, is to inform this anticipatory climate change adaptation. Another aspect of the science that underpins informing adaptation and risk assessment is the socioeconomic scenarios and the storylines that underpin those. This is from the fourth assessment report in 2007. Now, many of us who are climate modelers will be familiar with these scenarios in terms of emissions scenarios. This is back in the days when we had the scenarios called things like A1B, A1FI, B1, and so on. And now they've been replaced by the RCP scenarios, the representative concentration pathways, and the SSP-based scenarios, shared socioeconomic pathways. But this is the older ones. And it's interesting, there's different categories of the kind of global economy and the global population future and the strength of governance and so on in this kind of matrix here. But I realized that the scenarios that were used in the UK CP09 projections, the older UK projections, which used the high emission scenario was A1FI, fossil intensive. The medium scenario was A1B, so a balanced energy sources between fossil and non-fossil energy sources. And the B1 scenario was the low emissions scenario. They all have the same population scenario. The one scenario is all the same population, and that's an important point, which has which is a crucial point of debate in the IPCC Working Group 2 plenary 2 weeks ago, was anything to do with population projections as a driver of climate change is extremely contentious. And the point here is it's not all about population; it's about largely the consumption per capita is a key point here. But we're familiar with this from climate modelers as being emission scenarios, but there's much more within this, so that the distribution of population, the levels of governance, the ability to adapt due to the amount of wealth and so on. And that comes into a lot of the adaptation studies. The way in which climate change links in and drives responses, the view of that has kind of evolved through successive IPCC reports. So again, this is one from the third assessment report with climate change driving impacts also affected by vulnerabilities, so how sensitive people and systems are to climate change. And the overall impact being also affected by exposure, people or ecosystems being in harm's way of the climate hazard, and then having an initial impact or effect leading to what's termed here the autonomous adaptation, which is largely the reactive adaptation which happens almost naturally, if you like. So an example would be in the farming sector. Farmers tend to be very responsive to year by year and season by season changes. So often that can be termed autonomous adaptation as opposed to planned adaptation. And then the residual net impacts after that. And this is viewed as leading to responses in terms of planned adaptation to reduce the vulnerability and inspiring mitigation to reduce human interference. But this kind of concept evolved into what's now quite an iconic figure from the IPCC fifth assessment report in 2014, what's called the propeller diagram, these being the blades of a propeller, of risk. So climate risk being comprised of the hazard, so the change in the physical climate state, often the extreme weather events, for example, but it might also be the long-term trending climate conditions, affected by also on the human and the natural system side, the exposure, as I said, who's in harm's way, and the vulnerability, how sensitive people and systems are to being impacted. And these are affected by socioeconomic processes, which also link to emissions and drive climate change. So that's how that concept has evolved. And this is still quite central now, this three-way composition of climate risk. It's not all just about the hazard, it's also about how sensitive people and systems are to the hazard. And on the vulnerability side, again, a statement from last week's Working Group 2 report, it is assessed that between 3.3 and 3.6 billion people around the world live in hotspots of high vulnerability to climate change. So almost half the world's population are potentially highly vulnerable. And that's defined in terms of, well, the global hotspots of high human vulnerability are found in much of Africa, South Asia, Central and South America, and small island developing states, and the Arctic. And the vulnerability tends to be higher in places which have high levels of poverty, or areas where there's challenges from governance, perhaps with limited access to basic services, so water resources, transport infrastructure, communications infrastructure, and so on. Places with violent conflict, places with high levels of livelihoods which are sensitive to climate, such as smallholder farming, fishing, and so on. So this is where the high vulnerability often arises from. And the Working Group 2 report, it showed a lot of evidence of where adaptation is being shown to be effective to some extent already. It gave a lot of examples, which you can take away as a positive message, that to some extent it is possible to adapt to climate change if warming is kept to low levels. Often this breaks down at high levels of warming, so it's still important to avoid high levels of global warming, of course. But adaptation examples for improving food security have been shown to be successful and effective. Things like improving particular cultivars, so crop types which may be more resilient to drought or high temperatures, using agroforestry, so using woodland mixed in with food systems, diversifying the landscape, particularly on farms, so you've got a greater set of options. For example, you're not putting all your eggs in one basket, and part of that is strengthening biodiversity, of course. But community-based adaptation is also shown to be important. So local people often know how their own farming systems are sensitive to extreme weather and long-term trends. So local knowledge and indigenous knowledge has been found to be quite crucial in adapting to climate change. And one of the other aspects that was assessed was the other benefits of these kinds of adaptation beyond just adapting to climate change. There's co-benefits for generally for improving food security, nutrition, health and well-being, and improving livelihoods. So this can help with the sustainable development goals, particularly the goal for zero hunger and good health and well-being. So there's benefits beyond just adapting to climate change. And the other area where adaptation is important is in urban areas and cities. So by the middle of the century, up to 2/3 of the world's population could be living in urban areas. So it's important to be thinking about how we can adapt these to deal with climate change. And again, options which have been shown to be effective in cities include having a mixture of engineering approaches and nature-based approaches within cities. So urban infrastructure along with green spaces and blue spaces, so lakes and water bodies and so on, which can have a local cooling effect and are good for well-being and so on as well. Using urban agriculture, growing food within the urban area, and having good social safety nets, people being able to look after each other and having a good system to enable people to help each other, and for local communities, local governments to be able to look after vulnerable people in times of extreme weather, to try and minimise the impact of a disaster. And again, these have been shown to have wider benefits beyond climate change adaptation, such as on improving public health and conserving ecosystems. And again, the sustainable development goal to do with cities is mentioned there. But it's also possible to adapt in the wrong way. So put in place an adaptation which is trying to do the right thing, but may have unintended consequences which are negative. And actually, I mentioned the doorless sea wall in my opening slide, but a hard sea wall isn't necessarily always a good thing because you can constrain the amount of coastal land available for the coastal ecosystem. I talked about migration of coastal wetlands earlier on. That's not possible if you've got a hard concrete sea wall. So in the case of Dawlish, the wall was already there, so they're merely upgrading it. But introducing new seawalls and other hard measures isn't necessarily the right thing to do. So there might be, there's many cases now of a sort of softer approach to coastal management and allowing for seawater intrusion and allowing for the coastal system to evolve as sea levels rise. So that's one area where it's important to have a good level of scientific understanding of what's actually happening and being able to look beyond the immediate impact to look at the wider impacts. So again, climate science can help with avoiding maladaptation by understanding the processes. Another area which climate science can inform adaptation is on attribution, especially extreme event attribution. Peter very briefly mentioned this earlier, but we relied a lot on this in the Working Group 2 report. A lot of the statements which enable us to link observed impacts to anthropogenic climate change have been through event attribution studies, where climate models have been used to look at how the likelihood or the severity of extreme weather has increased or changed due to climate change. It doesn't always increase. In some cases, some extreme weather events have been shown to have been made less likely by human-caused climate change, but largely they tend to have been increased in likelihood or severity. One example being the flooding last year in Western Europe, which killed over 200 people, and there the daily rainfall was increased by up to 19% by anthropogenic climate change. In 2019, there was a huge widespread drought in southwest China, which damaged huge areas of crops, affected many rivers and reservoirs, affected hundreds of thousands of people and livestock, with very large economic damages of $400 million US. And the precipitation levels, which were low, those low levels were found to be between 1.4 and 6 times more likely due to human-caused climate change. So you often can't say the event wouldn't have happened, but you can say that it's been made more likely by human-caused climate change. Another drought example in 2017 in North America, huge wildfires and again huge losses. But here I've put this up because the increased likelihood of the drought was due to increased evapotranspiration rather than rainfall. And actually the anthropogenic signal on drought is often through evapotranspiration, the hotter temperatures drawing more water out from the landscape. So agricultural drought and ecological drought has a greater confidence in the signal of human-caused climate change there. And that was actually a conclusion from the Working Group 1 report, that the attribution of drought to human-caused climate change. Climate science can also inform adaptation in terms of climate projections, which we've heard a lot about in previous talks. Here's an example of, this is the multimodal median, the central estimate from the CMIP6 projections, looking at 2 degrees global warming. It's an annual average precipitation. And as been mentioned by Jason, and actually in Peter's question earlier, often the future projections are increasingly framed in terms of levels of global warming rather than scenarios for policy relevant purposes, because policymakers often tend to find it easier to understand rather than some scenario with some code name. They understand 2 degrees warming or 1.5 or 3 or 4 and so on. And as Jason showed, the global temperature scales pretty well. I think it was Jason. One of the previous speakers showed that global temperatures scale pretty well with cumulative emissions anyway, at least the peak temperatures. And for many of the hazards, those also scale with global temperature. So some of the impacts can often be presented on terms of global warming levels. It doesn't work for everything. It works pretty well for extreme weather, but it doesn't work for sea level rise, which has a very long time lag, and some other types of impact as well. But increasingly, policymakers are finding it useful to see things presented on global warming levels. But the reason I'm showing this now is because a lot of what we can do with climate science is to make decision makers aware of the uncertainty in climate projections. And again, this has been mentioned in earlier talks. The uncertainties in regional climate are often very large. And if you use the multi-model mean or median, the central estimate for regional climate change and regional impacts, you may get a very misleading view. So this is the central estimate here. And say if we focus on Australia, the central estimate is for almost no change in annual mean precipitation. But at the wetter end of the projections, so the 95th percentile, there could be large increases in precipitation. But at the drier end, the 5th percentile, there could be large decreases in precipitation. And for adaptation purposes, it's important to be aware of the range of possibilities and not rely just on central estimates, especially if your system is particularly sensitive. So you need to take a risk assessment approach. If we can't give you a good prediction of what will actually happen, you need to take account of a wide range of possibilities. This is the key point for decision makers and policy makers, not to use just central estimates. And this leads to high levels of challenge for dealing with adaptation to climate change. In this map here, from last week's IPCC report, the brighter the colours, that shows the higher the level of challenge for adaptation. And this high level of challenge for dealing with water scarcity comes from both whether the water scarcity is projected to be increasing, but also whether the uncertainty is increasing as well. If there's a high level of uncertainty in future water scarcity, it's difficult to plan ahead for long-term water infrastructure projects and so on. So that makes it more difficult to plan. Just finally, I was going to just briefly touch on the climate change risk assessment as a bit and some historical background of this. The Climate Change Act 2008 set in place this duty for the government to report to Parliament every 5 years on an assessment of risks that climate change brings to the UK. And it's up to the Climate Change Committee to advise the Secretary of State on this. So this is a statutory requirement to do such a risk assessment. And the key question is how well is the UK adapted to climate change, and what should the priorities be for the National Adaptation Programme? So this is the purpose of the Climate Change Risk Assessment, is to inform the prioritisation for the National Adaptation Programme. And the key steps in this in the risk assessment were to look at the current and future levels of risk and opportunity, then assess whether these risks or opportunities are being managed with current adaptation, and assess the benefits of further adaptation in the next 5 years, and come up with a list of a classification of the prioritisation of adaptation. And the top level, the first step in that is informed by the scientific literature. So climate science can help a lot with new risk assessments on, particularly on perhaps narrowing the uncertainties that I talked about earlier on. But the second and third steps are the information on current adaptation often comes from engagement with the stakeholders responsible for the adaptation, so different government departments or private sector bodies such as utility companies and so on. So there's a lot of working with outside of the scientific community on assessing the risks and levels of adaptation. I'll skip that one in the interest of time, but the key point is we assessed 61 specific risks in 5 different categories: natural environment, infrastructure, health, communities, built environment, business and industry, and international dimensions. Several different risks within each of those. And to cut a long story short, we found that more than half of those risks are assessed as needing more action on adaptation. So the country is not adapted to climate change. And in fact, only 7 of them were assessed as not needing any additional adaptation action at this time. So the UK is not adapted to climate change. And in fact, to come back to the IPCC report to finish, the same conclusion holds globally. The IPCC last week concluded that action on adaptation has increased, but progress is uneven, and we're not adapting fast enough. And finally, the closing statement of the summary for policymakers of the Working Group 2 report is that the cumulative scientific evidence is unequivocal. Climate change is a threat to human well-being and planetary health, and any further delay in concerted anticipatory global action on adaptation and mitigation will miss a brief and rapidly closing window to secure a livable and sustainable future. And this is an evidence-based statement with high confidence. And I put this up because, as I said earlier, the scientists in IPCC are now being extremely clear about the implications of these reports. So there can be no doubt what the science is actually saying about adaptation and mitigation and the urgency of both. Thank you.
So we have to do it this way. Time for one very brief, quick question and quick answer. Peter.
I'm very interested to hear that extreme event attribution was very important in Working Group 2, related to what I believe Working Group 2 calls losses and damages. But to go from there to loss and damage is a big step. Discuss.
Offline, I think, mainly.
I think there's a lot to be done, and there's a lot of issues.
Yeah.
Yes, there is. Could I just briefly say that but you have picked up on an important nuance there, that the report talked about losses and damages in a very kind of conceptual way, as opposed to the political and legal framework of loss and damage with a capital L and capital D for deliberate reasons. But yes, this is crucial because this is about helping the developing world adapt to climate change, and the developed world having a responsibility to help that adaptation happen, really, and the science underpins that.
Okay, thanks very much. We now come to a recorded talk by David Warrilow. I hope this can now be played. And the talk is, has the societal response to climate change been adequate?
Well, good afternoon, gentlemen. I've been asked to consider the question, has the societal response to climate change been adequate? Well, I don't think it will come as a surprise to say, not really. But what I want to do in this talk is to unpick that and go behind the bare conclusion and think about how have we got to where we are, and why is it such a difficult issue to address. What I'm going to cover in this talk is, first of all, the international perspective and how policies and actions have been agreed, what impact they've had, are we on track to avoid dangerous climate change, why has more progress not been made, and what was achieved at COP26 in Glasgow last November, and what are the prospects for eventual success, and what is the UK's role in all this. This slide provides a short calendar of key events in the development of climate policy internationally. Although the First World Climate Conference did allude to the potential for climate change, I think the real impact of the scientific community on the policy community didn't really occur till the late 80s and is reflected in the IPCC's first assessment report and the Second World Climate Conference, leading in short order to the UN Convention on Climate Change, which came into force 1994. The Kyoto Protocol was an attempt to have more firm commitments for emission reductions, but it took a long time, almost 2004, before it came into force. And even up to that point, there had been little discussion on where we really needed to be in terms of emission reductions. And it's only on the Cancun meeting that a global goal was written into decisions, with 2 different groups suggesting 1.5 or 2 degrees as a limit to warming. Paris continued that and also noted that we should be having net zero emissions sometime in the second half of the century. And Glasgow focused more on the 1.5 goal and net zero by 2050, the 2 things being consistent, and a package of other measures to get there. So you can see that there's been about a 30-year period of development of climate policy. So after 30 years of climate policy, one might ask the question, what impact has this had in the real world? And if we look at the CO2 concentration in the atmosphere as shown by this particular record at Mauna Loa, the very famous Keeling curve, we see that there's been a steady increase in CO2 in the atmosphere, which is ongoing, and very little indication that that increase is slowing down. If we look at the historic emissions of CO2 globally, we see that there's been a pretty relentless increase in emissions, perhaps a slight slowing down in the last 10 years or so, but nevertheless not a very dramatic one. Even the COVID pandemic has only created a little blip in the overall level of emissions, and there is some signs that emissions are increasing yet again. This graph shows the emissions that are coming from the top 4 global emitters, and the Western countries, like the EU27 and the US, have both peaked some time ago and are now beginning to decline. So they are taking action, and we are actually beginning to see an impact in their emissions. But at the same time, the big developing countries, most notably China, has accelerated its emissions enormously, partly through its accession to the World Trade Organization, and has grown in enormous amounts in the last 20 years. There's a steady rise more widely. All the others include Russia, Japan, the UK, and some of the other big developing countries like Brazil and South Africa. So the long and short of it is that although we are beginning to see some response to policy in the Western world, overall the trend is generally upwards, particularly in key developing countries. So the question arises as to why progress has been painfully slow. Well, there have been attempts to slow everything down by some vested interests in generating scientific uncertainty and misinformation. But I think that the more fundamental issue is that fossil fuels are seen as fundamental to economic growth. And also there has been a perceived high cost of mitigation. Developing countries resisted having reduction targets and were concerned about lack of financial support in the convention. And the US withdrawal from Kyoto and Paris, although they've now rejoined, due to lack of universal targets and other political concerns. So when one of the major Western, or the major Western emitter blows hot and cold on climate change, it's little surprise that others are less enthusiastic as well. And all along, there's been strong pushback from fossil fuel interests. And in the international process of the UN Convention, progress has to be by consensus. So that means that you are not likely to do anything that's quite challenging. And of course, for quite a long time, there was no long-term goal. So there was not the focus that we've got now. It's worth noting that the ultimate objective of the convention, that is the Climate Convention, is to stabilise greenhouse gas concentrations in the atmosphere at a level that would prevent dangerous and anthropogenic interference with the climate system. But it took until about 2009 or 2010 before that was actually quantified in terms of a temperature goal and any other aspect that would require specific action. And so we've gone through at least half the time of the policy development without having a clear idea of where we're heading. The Paris Agreement of 2015 put in treaty that global temperature should stay below 2 degrees above the pre-industrial, but that we should try and get it down as low as 1.5 degrees above pre-industrial. This reflected the divergence of views between the developed world and the most vulnerable countries who wanted a much lower target. The long-term goal for near net zero emissions in the second half of the century was actually an important innovation. It's consistent with keeping temperatures below 2 degrees or 1.5 degrees. And in fact, basically, the sooner you reach net zero emissions, the lower the temperature goal you can achieve. So what does this goal mean for emissions? Every year, the UN Environment Programme has published what's called a UNEP Gaps Report, and it shows where countries' emissions need to be at a global level by 2030 if the long-term goals are to be achieved. And this is the most recent version, a sort of re-engineered from the Carbon Brief. And basically, it shows that we're well above, if you look at the orange line, where we need to be in 2030, which is either the black line to get to 2 degrees or the greyish line to get to 1.5 degrees. And this has been referred to as the minding the gap. And although recent commitments by countries bring the line down a little bit, it still falls well short of where we need to be. Well, this was the situation going into the Glasgow meeting in November, and new commitments were made by countries on what they would try and do by 2030. And some also announced new plans to achieve net zero emissions around the middle of the century. There were specific commitments on phasing out fossil fuel subsidies, reducing coal use, reversing deforestation, and reducing methane. And there was a number of other things, such as technical rules to make the Paris Agreement operable and financial support from developing countries, which didn't go as far as some would have liked. So as the various new commitments came out, a number of analytical groups were busy trying to work out what it would mean for achievement of stabilization of global temperatures. And pre-COP in 2020, we were looking at temperature rises of maybe up to 2.6 or even higher, taking into account climate uncertainty. And that had improved a little bit just before the COP, and again improved a little bit at COP26. But of course, this is taking the commitments down to 2030 and continuing them at a sort of linear fashion to zero over quite a long time. But that's probably quite an optimistic thing to do. But nevertheless, that's the results that you get. Now, if you add in the net zero promises that a number of countries have made, then that has a bigger effect because, of course, if you go to net zero by 2050, that really does curb your emissions. And we can see that pre-COP, it was about 2 degrees, and after COP26, about 1.8. But again, I'd emphasize that these are quite optimistic because countries can make all sorts of commitments about 2050. It won't be the same people around to fulfill them, and lots of things can happen in between times. So, you know, these are the possible scenarios, but they're probably a bit optimistic as well. An interesting feature of Glasgow is the evidence that the costs of renewable technology continue to drop quite steadily. Solar PV has come down a long way since its inception in the early part of the century. And I was very conscious at Glasgow that there was a number of companies who were really working hard to think about how to reduce emissions, how to reach net zero, how to really rethink the way we do things. And that is a welcome development from the point of view of tackling climate change. So are we going to achieve 1.5 or 2 degrees as a temperature rise limit? Well, I'm not going to give you a definitive answer on that because there are too many imponderables, but on the positive side, we can see that, as I've just mentioned, low energy technology is coming in faster and cheaper than expected. There's lots of investment and employment opportunities in renewables, and there are a lot more non-state actors being active in climate change. And we have an agreed global targets and international structure and a growing public awareness, all of which will help push emissions down. But on the other hand, we have current commitments falling well short, so we've got a big job to do. Unprecedented rapid emission reductions are required, and there's always an upfront cost in doing these things, which means there's quite often a lack of political will and leadership. And unfortunately, fossil fuels still reward investment. The international processes are slow, and there is a need for common action, and there's also the problem of technological inertia, and indeed diversions such as wars and viruses. So what's happening in the UK? Well, the UK has taken quite positive actions to reduce emissions. We have a Climate Change Act, which means that government will be held to account by Parliament. We do have a net zero emission target of 2050 for the UK, and our progress towards that has been monitored by the Climate Change Committee on 5-year budget periods, and indeed by Parliament. Our emissions are now about 40% lower than in 1990, and we also have been developing our approach to adaptation through risk assessment and adaptation planning. This graph just shows how UK's emissions have been falling since 1990. The green line is the territorial emissions. That's the basic one that we have to report to the convention. The residential emissions, which include aviation and other factors like that, is the orange line, and the blue line involves trying to assess how much carbon we effectively import in all the material that we import from overseas. But in all measures, emissions are dropping, particularly those that are related to the UK's own activities. UK has also published a 10-point plan of actions for dealing with climate change, and also a net zero strategy, which is related to the 10-point plan, which was just published before the Glasgow meeting. Not going into the details of this, but it's important to notice that these plans do exist. If there's been a criticism, it's that it's all very well to have all these nice plans, but are the decisions at the working level being taken that are consistent with these? And there has been some concern that things are not really moving and being put in place that need to be put in place to actually meet these plans. Well, this talk has been largely about greenhouse gas emissions, but obviously climate change is still going on and probably will for some time yet. So we need to think about adapting to climate change, and we do have an adaptation plan, and we do have a sequence of risk assessments. The next risk assessment has essentially been done, and it will be laid before Parliament in 2022, and the next adaptation plan is in 2023. So the UK is working on this, but a lot needs to be done at the grassroots level. And according to the Climate Change Committee, the UK is less prepared for the changing climate now than it was when the previous risk assessment was published 5 years ago. So that's quite a sobering message. Well, now let's wrap all this up. Climate actions and negotiations over the last 30 years have had very little impact on slowing climate change, even though emission growth may be slowing. Increasingly, countries are committing to achieving net zero emissions in the next 30 years, but can it be done? Stated emission reductions commitments for 2030 fall well short of the pathway to net zero by 2050, putting the 1.5 and indeed the 2-degree target at risk. But, as noted, non-state actors are increasingly active and innovative, and many low-emission technologies exist, and costs are declining rapidly. Still, it's hard to shake off dependence on fossil fuels, as we have seen with the recent discussions on the cost of oil and so on. Adaptation measures are increasing, but progress is uneven, and there are reserve gaps, not just in the UK, but more widely. Thank you.
Catherine at the back, can he take a Zoom call for one question, or is that not possible? Not possible. I just want to congratulate David Warrell on that talk. I thought that was exceptionally clear, actually. So I'd now like to hand over to Brian Hoskins, who will chair the discussion group.
So we have a panel now, and they're arranged before you. And I don't think I need to introduce them. Who hasn't been? John Mitchell has not been on there. So John, and his name's been mentioned a lot. And then Keith Shine always mentioned a lot down there. So everyone else, you know. I thought we would start while you're thinking about some questions for this elegant panel here. We'll just start with 1 minute or possibly 2, depending on whether you've spoken before. Just any thoughts at the end of today, things you didn't say, or just some reactions to what you've heard. So we'll start from this end. Tim, would you like to, do you have the microphone? Yes, you do now. So any thoughts at the end of today on what you've heard or the topic in general?
Well, I guess that by dividing it subject-wise, sometimes you lose the developments in how things are integrated together. I gave one example in my talk about observations and models being integrated in reanalyses, which are really widely used. But I think you could make the same claim in various other aspects as well. So at the end of Joe Hayes' talk, she talked about the recent IPCC report and the narrowing, quite dramatic narrowing of the uncertainty and climate sensitivity, which will impact upon a narrow range of possible future projections as well. So it's really important. And I think that's come about by bringing together understanding and evidence and data from not just models, but also from paleoclimate, from instrumental records from all parts of the climate system, not just the global surface temperature I talked about. So I think that kind of integration is something that we should also be proud of in terms of the developments in the history of climate science. Whereas when we spoke about it, quite a lot of that was separated into compartments because of the way that we were speaking. So,
okay, thank you. Thanks. John.
Okay. I don't have a lot of comments to make. One thing I would just like to say a little bit about it is the start of climate modelling in the UK, because it did happen actually before Mrs. Thatcher in 1988. And there's a nice history by John Agar in the 20th century of British history in 2015, which I've taken some of this from. And he starts in the early 1960s, 1970s. And then there was work in the US. Note we've heard about GFDL on working on CO2 and climate, and bodies diverse as MIT and even the CIA. And of course, there was an interest in the press. In the UK, the Met Office was doing modelling. It was doing numerical prediction of climate. It also had general circulation models, but it hadn't models which are really suitable for that sort of climate change. And they hadn't done any model experiments on CO2, certainly not GCM experiments. Where environmental interests at that time were growing, there was the publication of Limits to Growth, and a general interest in would CO2, increasing CO2 affect climate. And at that time, the Heath government created the Department of the Environment, and that was fairly critical because up to then there hadn't been really a government department focusing on things like the environment and climate change. And they had an interest in finding out did this make sense, so they convened a number of meetings, and John Mason, who was then the Director General of the Met Office, attended those meetings, at least one of them. And there was a feeling that the British government would like to do something to have its own opinion on climate change, and it should do something. My impression was that John Mason was actually quite skeptical about greenhouse warming, but I think he felt if anybody is going to do any work on it, it would be done in the Met Office. Shortly after that, at that time, I was actually, although I'd been working in the dynamical climatology branch, I'd been sort of seconded forecasting for 18 months. So I was doing things like writing the shipping forecast. And one day I came in and I was told, well, actually, you're going to finish that. We're going to do some work on CO2. We want you to do some integrations. At that stage, I think I was only given one member of staff, and we'd like you to do it as soon as possible, like starting now. And so I did a number of experiments with a model. I had only 1 year run, 1 to 2 year runs of a 5-layer model. And amazingly, those actually were referenced in the Charney report in 1979. You'll actually see a reference in there. I think they're the worst design experiments I ever did. And I think that really steeled me to saying, right, if the Met Office is going to do this, we're going to have the right models to do it. They're going to have to be the right resolution so we can run them long enough. We're going to have to be coupled to the ocean, and we'll have to do credible experiments. And that's what I spent the next 10 years doing. And by the time it came around to Mrs. Thatcher's announcement and the idea that we were maybe going to have a European climate centre, or it ended up being a British climate centre, we were well placed for that. So sometimes bad things can actually help. The second thing I'd just say very briefly, one thing was evident that the conversations between government and science weren't great at that time. So when the Hadley Centre was set up, the way the contract was managed was that we had a 3-year rolling programme, and it was reviewed every year. And we met with, so the group leaders in the science, led by a Hadley Centre coordinator. First one was David Bennett, the second one was Jeff Jenkins. We met with DOE staff and we discussed the contract. And that did two things which I think were very important. One, it helped the government scientists, the government staff understand more about climate change and kept them up to date. Because it's not just done annually, we met with them certainly about once a month. But the second thing it did, it meant the scientists had some idea of what the government wanted to get out of the program and what the policy things were and what things would work and what didn't. And that worked very well for the time. The main problem is that the DO staff tended to move on. So having educated them in climate change, you get a new person in managing the contract and you had to start all over again. The final thing I want to say was just spreading the data. So it's all very well, the Hadley Centre having this great conversations at the government and producing the data. But when it came to the first IPCC report, I think there were only probably about 5 government institutions involved in the modelling, and the data was not widely spread. But worse than that, the modelers who were involved were expected to evaluate the models, and that didn't work for a couple of reasons. One, we've already got enough to do, and secondly, it's very hard to say to a nation, well, actually, we can't use your model result because your model is rubbish. You could give rise to an international incident. And I just want to pay credit to Larry Gates, who set, first of all, the atmospheric model into comparison. He was also chair of a WMO modeling group, and he set up the coupled model into comparison experiment so that the data was sent into one center. PCMDI, the Institute of Lawrence Livermore, held the data, and he got together staff, and they did assessments of the models. And that made a huge difference to being able to evaluate the models. It helped the modelers in that they didn't have to do it. They had it done independently, and the model data was actually made available not just to government institutes but to academia. And in fact, Larry went on to agree that PCMDI would also take in data from model experiments that were run explicitly for IPCC experiments. So not just the control simulations to evaluate the models, but also the actual integrations that would be used in the IPCC assessments. And that, manyfold increased the number of people who were looking at data, improves the assessment of the data generally. And I think we should pay tribute to Larry for that, because that made a big difference to what was available. Sorry, I haven't been too
Okay, thank you, Tom. Yep.
I'll try and do a brief one. So one thing that I don't think we've talked about so much today, we have been talking about risk and risk management because that's what mitigation and adaptation is. But we've been focusing purely on the physical risk. I think we've started with some of the things that Peter was discussing and Richard with loss and damage to bring in the fact that there are other risks. So there's litigation risk, for instance. That's very strongly, I think, tied to blame and attribution. There's also transition risk and thinking about how the policies that are put in place themselves have an effect. When we try and manage risk, it's really important to include that wider basket, that full basket. And I think we are getting better at that. So we're seeing things like TCFD being put in place.
Sorry, TCFD.
Task group for financial disclosure. It's basically reporting on companies' risks, and it starts with the idea of bigger companies going through this process of disclosure, but moves to a wider set. So I wanted to mention that. The other thing I wanted to mention is the idea of trade-offs and co-benefits. And when we see the debate and we look at the consequences of impacts, sure, they are really scary numbers. They're really big numbers. But we also need to look at the positive side of that and look at the co-benefits of action. So when we look at mitigation, there's also the impacts on energy security. There's also the benefits for well-being. And I think this is a part of the debate that really hasn't come across as strongly as it needs to date. And since I didn't have time to put in my talk either, which is probably symptomatic, I thought I would mention it now.
I think we're seeing one of the co-benefits we should have had of energy security now if we'd gone to renewables earlier. Thank you. Keith.
Yeah, thanks. Yes, I wanted to make 2 points, which is more than my football team has managed this afternoon. I guess my comments are maybe aimed at younger members of the audience, which I hope are out there in the ether. Is that I think it's useful to look at the history of development of our subject, because when you enter a subject, you can sometimes get the feeling that what we know now has been known for ages. Whereas, as we've seen today, there's been a lot of evolution of understanding over these past 2 or 3 decades. And one simple example, which I think Jason talked most about, was the carbon budget and the concept of net zero, which is surprisingly recent in terms, although you can trace the history back quite a long way, in terms of the wider awareness is quite recent. And actually, a lot of that understanding came from rather simple models as well. It's not from big models that you needed. So I think it's always useful to look back at the evolution and realize that some of the stuff we're doing now was actually found out quite recently. Another thing, and perhaps a bit more controversial, for some people is in some quarters there seems to be too much of an emphasis on the way forward in climate modelling is building more powerful computers, and that should be the priority. And I personally find that a depressingly technocratic kind of view of climate science. So if we want to solve these problems, we just have to wait for a bigger computer. And we've seen today there's some very stubborn areas. I think Joanna mentioned, the evolution or lack of in understanding of the equilibrium climate sensitivity. And Matt showed a very telling slide about precipitation bias and how that really hasn't gone away as our models have become more sophisticated and finer resolution. And I guess, we need to take a really balanced view that we need better observations, more sophisticated ways of analysing those observations, conceptual understanding, as well as more powerful models to move us forward. So there's an idea.
Well, thank you, Keith. Perhaps we should remember when we talk about sophisticated climate models, that sophistry is actually too much complexity. So, yeah, quite. Yeah. Okay, right. Thank you, everyone. Now we come to questions from the audience. And there's a very specific one that's been given to me, presumably from the web. So there was a rapid warming at the end of the Younger Dryas. Is it possible that a repeat of that event could be an inevitable surprise? I'm not sure about an inevitable surprise, but anyway. Has that been modelled yet? So the warming after the Younger Dryas, does anyone on the panel want to talk about that? I'm sure, John, you can.
I think the answer to that is I don't know. I'm not a paleo modeler, so I'm not familiar with the work that's been done in the Younger Dryas. I think we did talk about on Antarctica and ice ages and the end of ice ages and water coming out and it being very dependent on the amount of water, but not just that, but specifically where it goes. And I guess having the underlying ocean circulation right. So, I mean, we do need to be, what's the word, not modest, but not to be arrogant and think that we understand everything. So these things are always a possibility. And I'd agree with Keith that it's not just trying to be bigger and bigger models, but actually trying to understand why the models behave the way we do. Because the whole advantage of having a model is that you can play with it and you can look at it and you can change things and you can gain understanding. You still have to use your judgment as to whether that understanding applies to the real world. But I think we should always be open for surprises.
Anyone else want to? Tim?
Okay, I'll just make a brief point that some of the abrupt changes in the past tend to occur when there's a lot of ice around or a lot of ice remnants as it's melting. So, some of the events in the glacial periods and then the deglaciation period come from the rapid release of meltwater that's ponded up behind disintegrating ice sheets. So that particular scenario isn't what's happening now. It doesn't rule out other types of abrupt events.
So generally the warmer periods in the Earth have been more stable than the colder periods. That's very.
Is that a statement or a question?
Well, it's a bit of both, I think. Right. Okay, let's move on from that. And the question over there, I think.
Thank you. Vladimir Jankovic from University of Manchester. I'm a historian of science, and I'm standing partly because I think that I'd probably be more intelligent if I speak and more articulate. And the question is, I think, initiated by both Jason's comment, the last comments that made, and also David Waterlove's question and analysis about the successes and failures of climate policy. And one of the things that I was going to raise was the publication of 2010 by late Steve Rayner, who's known as the Hartwell paper, in which he and a group of authors criticized the Kyoto Protocol for misdiagnosing climate change as an environmental issue. Instead, they suggested that climate change was a developmental issue. that the focus needs to be on the society and economy rather than pure science and environmental framing of it. And the reason why he identified as misdiagnosis was that they observed what I see as a fallacy of identifying climate change as a tame problem. Now, the difference between the tame and the wicked problem comes from 1970s policy literature initiated by Rittel and several of others in which they claim that there are certain issues called wicked problems that cannot be easily solved because there is no stopping rule. And the reason why there was a problem with the Kyoto Protocol is that the Kyoto Protocol assumed that there was a stopping rule in the case of climate change, which there isn't. Instead, they claim that climate change is a wicked problem that needs to be dealt in a very different manner. And they thought that the different approach to this, which they spell out in that short paper in an interesting and kind of very creative way, suggested an alternative to Kyoto, not necessarily to be implemented, but as an idea. Now, that's the background. And I'm just wondering, there is a question behind all of this sort of introduction. And the question is the following. If we take a perspective of the potential future peril associated with increasing CO2 concentration, then clearly we can say that we have failed. But if we look at the perspective from the perspective of the complexity of the problem and the nature of the beast from the point of view of the wickedness, then can we say that we have actually been successful?
Okay, right. I don't know whether you've read Steve Rayner's paper or whether you'd like to discuss the wickedness of the problem. This is a bit past the microphone here, this game. I think it's stopped with you, Jason.
Yeah, I'll have a go to start with, I think. So I do agree that climate change is a wicked problem. I think it fits a definition of that. We do have quite a lot of debates in the SPF UKCR program, and one of the champions is I think very clear on how climate fits into that category. I think the linking to development is an interesting one, and I think we see that increasingly when we look at some of the overseas development funding and where that's going, and how that's being applied. And when we look at some of the successful interventions, they're not just targeting adaptation, they're targeting development, and they're trying to integrate the usually adaptation measures, but not always, into a wider context of people's standard of living, people's cultural background, etc. And so I think there is value in linking them. In terms of whether we've succeeded or failed, I must admit, I don't think in those binary terms. I think we understand a lot more about the climate system. I think we understand a lot more about the current human system and how to nudge it in one direction or another. I think we've learned a lot about a whole range of technologies that can help us in a whole set of ways. So on that side, you may say we've succeeded, but we're not on course to limit warming to 1.5 at the moment. We'll have to do much more.
Okay.
Yeah, it's a very interesting question. I think there's one way that we have succeeded. It doesn't mean that we're successful, but it's gone in the right direction. Is that we've had various mentions of scenarios here, the so-called business as usual scenarios, and then they've had different names. Is that we know some of those upper level scenarios are no longer credible. We're not going to go up what the first assessment report called business as usual, and they're being called SSP 8.5. That we're nowhere near those. So there is a world in the ozone area. They often talk about the world we've avoided, and I think we have managed to avoid the very worst. Although, as Jason says, we're not on track to meet the Paris targets. We're also not on track to meet some of the worst predictions that we've had over recent years.
Okay, an interesting question there. John, I'll move on to another, or do you want to? Okay, Simon, do you want to ask yours?
So, Simon Buckle, to build on some of those comments, actually, and to perhaps add a quick comment and a question as well, if I may. I mean, I think Steve Rayner was on something. I don't think it was development in the sense of development in developing countries. I think it's the whole economic, political, social system we have, in effect. So to get to the sorts of levels that we're talking about in 1.5, you need transformation of systems in a way that we don't really seem to be able to get to grips with very easily. I mean, look at the problems we've had in, the housing sector in the UK, for example, with programs there, or the way that our cities are completely dominated by car transport and vehicles. And it isn't just an issue of carbon externalities. These people are allocating public space. They're putting people's lives at risk, whether they're cyclists or kids, air pollution as well, more generally. And this is systemic. This is just normal. So we have to rethink, in a sense, what our societies want. And it isn't just GDP growth. This goes back to Jason's well-being point. And we have to think about the systems and where we can act to sort of accelerate change and to dampen negative changes. And we've had some positives there with the renewables and the slowing down of emissions from the electricity sector, but other sectors are really tough. And we know that the international aviation industry is just looking at, offsetting everything apart from, maybe a small amount. And that's going to drive, potentially positive, potentially negative changes in different areas, and particularly for indigenous people, for local communities living in areas that, the land is bought for offsetting. So I think there's huge issues that we're just not tackling within the system, and we're sort of not talking about. And then the question was, Matt's lovely diagram of the biases in the models, and then the discussions about the attribution. Very soon, the models are not going to be just models for academics. They're going to be models, and they probably are already, that are used in courts to ask for damages, for losses and damages from governments that have emitted or from companies that have emitted. And is the state of the models as it is sufficient to support that, given these biases and the judgments we make about attribution, or do we need different approaches? And I take your point, Keith, about, you can have too complex models and it tells you nonsense because you've missed out some key underlying process on which you've got not enough data or understanding. And maybe it's storyline approaches and dealing with the uncertainty through robust decision making. But what's your view on that whole nexus of issues? Simple question.
Right. So, what about these stubborn model errors? When it comes to the actual circulation changes, we have almost zero confidence in the circulation changes. We have those stubborn precipitation errors, which have been there all the time, whatever the resolution. Are these enough to take to the court where they'll say, oh yes, this is certainly due to your activities that they have this problem? Okay, who would like to answer that? John.
It seems I'm stuck with this. It's not a question I'd like to answer. I mean, these biases have been around, and I think the last one that Matt showed was 2003, was it? No, 2003. Yeah, and certainly goes back at the start of CMIP. You can see a lot of those errors. And I mean, the history of general circulation models is that when they first worked, we were really surprised how well they worked. And I guess there were some large-scale factors. I mean, you've got Hadley circulations, you've got the baroclinic zones, and those are fairly well defined. But when it gets down to detail, it's just very, very difficult. So in terms of reducing the errors, I think it's going to be very, very difficult. In terms of what one would do in a court when the barrister stands up and says, well, the error in your simulation is twice the size of the change that you're accusing my client of, I think you're going to have develop some clever methods of trying to allow for those biases. So I think there may be ways you can do it, but I wouldn't like to be up against a clever barrister.
Yeah. There's a good reason we've been dealing with anomalies often with models as well as with observations, because if we looked at the absolute, it would be no good. Yeah, Tim.
So just to add to that and say that it's not all just about models. Our kind of conceptual or theoretical understanding comes into it as well. And there are some aspects where you combine that with an observed change that's starting to emerge from the natural variability. And so in terms of precipitation, that was indicated as a bias in that. But if you're looking at some particular extreme events, then I think there's quite a lot more consistency between models and observations in the thermodynamic component, as a warmer atmosphere holds more moisture, and the event attribution that was mentioned, which is one type of climate science that might end up in court. What is the human contribution to a particular extreme event and the damages that ensue from that? Those aspects rely upon a combination of whether or not you can see these things emerging in the observations, as well as model simulations where you can do experiments where you can say, if we didn't increase the greenhouse gases from human activity, what does the model suggest? So it's not, I don't think the model biases are important to always bear in mind and make sure we're cautious, but we don't know everything, but we don't know nothing. And Matt would like to add something. Oh, question.
Okay, Matt, we've got 2 minutes left before I'm hoiking everyone off. So
this should be a quick fire one. If I were a young PhD student starting out on my research career, what would the panel suggest for my PhD thesis?
Not just Mars, is that right? Okay, who would like to? Keith, come on. Right, it's over to you. Right. Oh, John, can you pass the microphone there?
Yeah, that's been dropped on me. Well, I know in my particular area what I'd aim them at. I mean, there are details of the links between basic spectroscopic understanding, which underpins the radiative transfer schemes that are in our climate models that need more study. So, I think there's things on the boundaries of spectroscopy and atmospheric radiative transfer that deserve looking at.
Okay, is there anyone? Jason?
I don't know if you've got a good funding source, so I suppose we better make it good just in case. On one side, there's, around the physics, we still don't understand high-end sea level rise, and in particular, really understanding when some of the processes that will come into play that could accelerate sea level rise. So if it was a physical science one, I'd probably send them in that direction. If they didn't have that restriction, I would probably encourage them to go really interdisciplinary and try and do something that links the uncertainty as we understand it in the climate models to decision theory. I think that would be probably the most useful skill that they could then bring into the debate for us.
Right. Unless John and Tim, you have urgent answers.
Very quickly,
okay.
Something that Peter Stott and I looked at, must be about 16 years ago. The detection and attribution technique we use tends to scale your model according to the observations, and then you can extend that into your future prediction. So it's a way of possibly correcting models, at least at a global scale. And we tried to see if that worked or not. We had only 3 models. I tried to do some work a few years ago, but the models were just too diverse. It didn't make sense. I wanted to see if that method really worked.
Okay, right. I'm going to close it there because Chris, unless Tim, you do. Over to you, Chris. Thank you very much, panel, for the answers.
And thank you very much, audience, for some excellent questions. Actually, that's really hotted things up, if I may give it a small pun. So we need to stop now. I want to congratulate all the speakers. It was a very wide-ranging meeting, and I thought they covered the subjects magnificently overall. This is being filmed and recorded, so I believe it will be available at some stage for you all to look at your leisure. So if you missed anything, you've got no excuse for not catching up. Thank you very much.